Hi, I am Dr. Sreedath Panat, a PhD from MIT and one of the founders of Vizuara AI Labs. I am just recording this video after finishing the recording of this particular lecture, which is a dissection of the paper on vision transformers. So the paper came out from Google and it was in 2020. And they showed that pure transformer architecture in the absence of convolution can be used for performing image classification. It's like a seminal paper, almost 75,000 plus citations now. So I am recording this video not to give you an introduction, but to share some of the concerns that I felt while recording. So I have written a few points down. I'll just read some of those constraints, which I really want to address in this video at the start. First thing is, this lecture is definitely too long. I have written down a few points. I'm just reading from these notes. So one is, when I'm dissecting a paper, this paper is around 22 pages, counting references. So of course, I cannot condense this into a 30-minute lecture if my goal is to sort of do paper reading as part of this series. If my goal is to just teach about vision transformer, of course, I can ignore the paper and I can just talk about the model. That part is easy, but this was very difficult. While recording, I realized that the lecture was becoming too long. Second issue was I was getting tired, like speaking for a long time while reading and while processing and all that. It was actually very physically and mentally tiring. That was another thing which I noticed. Another thing which I highly suspect, which will also happen to you while watching this lecture, is that you will also get physically tired and mentally saturated, because you can't sit down and hope to finish a paper in just one sitting. It's like wishful thinking. So what I realized for myself is that, even while recording, I'm mentioning this once more, is that I will not record in one sitting because that will truly drain my stamina, but I'm recording it in multiple sittings. I'll take breaks whenever needed. To drink water or bathroom break or whatever. I highly recommend you also to take breaks and try not to, kind of over ambitiously finish this paper in just one sitting. It will be too difficult. Second thing is, I have a printed copy of the vision transformer paper, which I am reviewing in this lecture. So I initially went through the printed copy by, it's a totally different feeling. Like I just put a pen and marker and just went through this copy from first page to the last page, covering everything. And only then I started recording the lecture, once I went through everything by hand. What you could do is, if you have access to a printer, or if you can just take a printed copy, it will make you feel so much better to have a physical copy in your hand and, go through the paper line by line. And you can play the video, my lecture, on the side so that you can listen to my own interpretations of the content that is there in the paper, right? So I highly suggest you this. Another thing which I was doing was, I'm also reading this book by Cal Newport, Deep Work. I have already read this maybe 3 times in the past. This is my perhaps 4th reading. I so much love this book because the kind of concepts that are mentioned. So the deep work hypothesis is, they have a, one sentence hypothesis. I have just marked it in page number 3. So here I have just marked it. It says, deep work, professional activities performed in a state of distraction-free concentration that push your cognitive capabilities to their limit. So to record this lecture, I really had to close my door and I just had to ensure that nobody will enter the room. No distraction is there. My phone is on flight mode and everything. These efforts create new value, improve your skill, and are hard to replicate. So I kind of resonate with this a lot. This is an amazing book. I highly recommend you just reading it. Cal Newport has written it in such a nice way. And it sort of makes you appreciate the fact that, to do hard things like reading a research paper, you really have to spend time. It's difficult. You will get tired. You will get saturated, and then you have to overcome it, right? So there is no other way around. If your goal is to read the paper, if your goal is to just understand about vision transformer, there are other YouTube videos which you can watch, which has got nothing to do with paper. They will refer the paper, but you won't be going through the paper line by line. So that is one thing. So few of my concerns was, or constraints was I have to read the paper. I have to read the paper during the lecture. Otherwise, it will not be a paper reading lecture. It will be like it will become like a PowerPoint presentation of vision transformer, which I don't want to do, which I have already done in the past, and it's with a different psychology. Here, I really want to incorporate reading. Second is I really want to dissect what is written in the paper, not just the concept, but the writing itself. Not the idea of vision transformer, but I really want to go through the text in the paper just so that we are spending enough time on the writing. So I don't want to make things brief for that reason. And because of this, the lecture video is going to be long. That was the second thing. Another thing is I want to keep the paper structure intact. So what do I mean by that? I don't want to convert the paper into like a paraphrased shorter format or anything like that. I don't want to convert this into beautiful images on a PowerPoint presentation. I know that that is what will be more convenient to most people who are watching. I'm fully aware of that, but that is not my purpose. Here the purpose is to read the paper itself, not to read a watered down version of the paper. So I wanted to keep the paper structure intact. And then I was like, there were certain feelings that I was getting. Like one was, why am I doing this? Why do I read this paper? So I have two purposes. One is to improve my own paper reading habit. I want to cultivate this habit so that I can carry it forward for lifelong. Second is I really want you to also cultivate this habit if you are kind of following along with me. And I don't want to punish myself so hard if I feel like I'm getting tired or saturated. Those feelings are quite natural. So I just wrote it down here just to make sure that if you get those feelings, I just wanted to say this out loud so that if you get those feelings, it's fully natural and we should not be too harsh on ourselves. Another thing is importance of taking breaks. So this I already mentioned briefly, but if we don't take breaks, this is not going to happen. You will never ever finish this in one sitting. I'm 100% sure of that. I could not manage recording this in one sitting. It's very tiring. It drains a lot of energy. So it's almost like a marathon, right? You have to maybe eventually in future you could read one paper in one sitting, but usually it's difficult. So, and I will also assume that the viewers of this lecture are adults who do not require spoon feeding. Like you have enough self motivation. I'll try to motivate whenever I can, but I don't want to treat people as kids. I want to treat people as adults who know what they are doing, right? So, and I assume the reason why we are watching this lecture is because you want to learn how to read research papers and you want to cultivate that habit also. The next point is use ChatGPT abundantly. So what I mean by that is, so papers are information dense. Every paper has a lot of things, and maybe you will be lucky if you understand half of the things in the first read. It always happens to me. So how do I try to understand the rest of the half things? First, we have to agree that we don't know everything, and wherever there are paragraphs or sentences which do not really make sense, feel free to ask ChatGPT. Take a screenshot and put it on ChatGPT and ask the question. The more important thing is to ask that question so that you are acknowledging the fact that you don't know it fully, and you are ready to understand it with the help of either a person or ChatGPT or Googling. And then I also wanted to write on the paper, just like how I'm writing on the paper. Like when I'm reading it, I'm writing and annotating. Just like this, I want to do it. So I'm copy pasting the pages of the paper onto a Miro board. And yeah, and then one more point which I added for myself is once I finish recording, I will add snippets like this, which kind of put my thoughts on the paper, which I forgot to mention during recording. So this video snippet which you are seeing right now, I recorded after recording the lecture. So these are some concerns or thoughts that I had. Oh yeah, another important thing was, should I care about the video length or not? So this was a thought that I had for quite some time. Should I split this video into multiple parts, or should I just keep it as one single video of multiple hours? Then I thought, okay, let's not divide it into parts, because I could then divide paper into parts. I could then divide paper into 200 slides. So then where do I draw the boundary? If I'm dividing the paper into parts and putting out it part by part, I'm not really doing justice to the fact that reading paper is difficult, right? So I'm not saying it has to be difficult, but that difficulty I have to go through myself, and perhaps whoever wants to read the paper, you have to go through that difficult idea that paper reading and going through it is a hard process. So I did not want to chop this lecture into multiple lectures, which would have been convenient. I know it would have been convenient for me to record. It would have been convenient for you to follow. But if I did that, I think it will drain the very essence of this paper reading process. So these points I just wrote down on a page and I just wanted to communicate with you. But other than that, I am pretty sure after this process of, a long tiring session of reading through the paper, you will derive a lot of satisfaction. I'm internally feeling it. I'm feeling very satisfied with this process that I have set up now, and I do plan to continue this process further going ahead. So I also hope you will enjoy along with me. You will get tired also along with me, but I hope you will also enjoy the process. So enjoy this paper. Let's get into the vision transformer paper. Hi, welcome to a new lecture from the Reading Research Papers series. In today's lecture, we are going to be picking a very famous paper on vision transformers. So the paper is titled "An Image is Worth 16 by 16 Words, Transformers for Image Recognition at Scale." This is probably the most famous paper on vision transformers. Right now, it has more than 75,000 citations. A couple of months ago or 3 months ago, it was, I think, 63,000 citations. So it's rapidly growing. I'm sure this will be one of the highest cited papers in the domain of vision transformers. This paper came out from Google, and they showed that the same transformer architecture which was proposed in the Attention is All You Need paper could be used with very little modifications for images as well. So you can access the full paper on arXiv. You just need to Google vision transformer paper, and most likely this will show up. The link to this paper will show up. This paper was presented at ICLR, and it's a very nicely written paper, around 22 pages. So what I'm going to do here is I'm not going to water down the paper, and I'm not going to just present you a summary. I'm going to present you the entire paper. So what do I mean by presenting you? I simply mean I will read through the paper line by line as if I'm just conducting a reading session. But I have read the paper already multiple times. I have implemented vision transformer from scratch, and here in my notes, I have basically dissected the entire paper. I have laid down most of the doubts or questions that you may have as somebody who is going to read the paper for the first time. But don't worry about any of that. My goal is to take you through the entire paper. It is not to present you a summarized or kind of easy version of this. I don't want to make it too easy, because one of my purposes of this lecture series is to kind of impart the habit of reading, especially the habit of reading research papers, into those who are interested. So of course the lecture is going to be a bit lengthy, but I also assure you at the end of it, it will be very rewarding. And by the end of the lecture, you will gain some significant amount of confidence that you can also read papers like this, maybe starting with this vision transformer paper. So the 22 pages also include references. So you can think of the paper as slightly less than 22 pages. And up to, I would say the main paper is up till 9 pages. Remaining some pages are references, and then it's supplementary. Some sections in supplementary is actually important and interesting, so I'll walk you through that as well. But you can consider the main paper to be roughly 9 pages. So not a very, very long paper, but really nicely written paper. I have always enjoyed whenever I have read this paper. The figures are very nice. A lot of things are self-explanatory, and a lot of things are not. So the original architecture was proposed in 2020, but I think the paper was presented in the conference in 2021. And I think the version that we are seeing right now, which might be an edited version in arXiv, I have to check. It's from 2021. So what I'm going to do is I will assume as if I'm also seeing the paper pretty much for the first time. I will read from top to bottom. You can also read along with me, or you can listen to me read. If the reading part is not so helpful to you, you can skip the parts where I read, or maybe make the audio muted or whatever is convenient for you. But I'll be reading this as if I'm reading in front of a classroom. And whenever I get some doubts. Many of my doubts are already cleared because I had spent enough time on this paper. But if I get some doubts, I will pretend as if I am sitting with you to figure out what some sentence is trying to say. So maybe we can take a screenshot of that particular sentence and ask ChatGPT to understand things better. Basically, this will show you how you could also read research paper from scratch, even if you don't have any experience reading papers. So with that, let's get into the lecture. So if you look at the authors list, you can see that they are from the Google Brain team. The Attention is All You Need paper was also from Google. Ashish, Vaswani, and others. So it's amazing that many of these seminal papers are actually coming out from Google. This paper, if you want to see the number of citations, you can just search Vision Transformer paper, and then you can see that this one has 75,000 plus citations. It's amazing for a paper that is relatively recent. So let's look at what the abstract is saying. So what I suggest you do is you can also have a printed copy of this paper with you. I in fact have a printed copy with me. So first I read through the printed copy. I took a pen and I marked down points where I had questions, and then I asked the questions to Google or ChatGPT, figured out answers, and then that's how I read through the paper. You could also do the same. You can have a printed version yourself, or you can follow with me in this lecture, but while taking notes, so that way you will not forget a few things later when we reach the second half of the paper. So the abstract says, while transformer architecture has become de facto standard for NLP tasks, its applications to computer vision remain limited. In vision, attention is either applied in conjunction with convolutional neural networks, CNN, or used to replace certain components of CNN while keeping their overall structure in place. So this second sentence is important because we know that convolution as an operation is so important in images because it captures two-dimensional features. So convolution filters are matrices like this, something like this. This is a 2x2 filter. And this filter performs some kind of mathematical operation on top of images. Images are also pixels, which you can arrange like a matrix like this. So because of the fact that these convolutional filters are two-dimensional, the convolutional neural network, which performs a series of these convolution operations, can extract 2D features from images. So it was very difficult to imagine something that does not involve convolution operation to perform really well on images. So that was one of the reasons why from 2010, maybe till 2020 or so, convolutional neural networks really dominated deep learning, especially for vision tasks. So here what they're saying is attention is not applied independently. It's applied either in conjunction with CNNs, or some components of CNNs are removed and somehow attention is introduced. This is what people have been doing in the past till this paper came. And what this paper shows is that we show that this reliance on CNN is not necessary, and a pure transformer applied directly to sequences of image patches. So we have to understand what does sequence of image patches mean here, which we will soon understand. But basically CNN or convolution is not necessary. We can apply a pure transformer. What do they mean by pure transformer? An architecture that sort of looks like this. So here, this is a pure transformer architecture. On the left hand side, it is a BERT-like model, encoder model. On the right hand side is GPT, decoder model. And these two are transformer blocks. These gray color blocks are transformer blocks because you can see multi-head attention. You can see the multi-layer perceptron feed forward neural network. So what this paper is arguing is that a pure transformer can be directly applied on sequence of image patches, and they can perform very well on image classification task. So if you think about what this paper is trying to teach a transformer to do on images, is vision transformer directly applied for classification tasks. We'll see through the course of this paper whether some other tasks which are not classification, whether object detection, basically drawing bounding boxes around images, or image segmentation, whether they are possible using this or not, we'll see. Then One more argument that this paper is making is when pre-trained on large amounts of data and transferred to multiple mid-sized or small image recognition benchmarks, Vision Transformer attains excellent results compared to state-of-the-art CNNs. And it does this while requiring subsequently fewer computational resources. So if we train the Vision Transformer on big enough data set, and when they say big enough data set, they don't mean the usual ImageNet data set or usual CIFAR 100 data set. So CIFAR 100 is this data set, which I guess has 100 classes. They are very low resolution images, and they have classes spanning various natural objects, images, etc. ImageNet is also a similar data set. So ImageNet is very famous. It was part of many competitions. So ImageNet has, I think, a big data set as well as smaller version. Bigger one has, I think, 21,000 classes. Smaller one has around 1,000 classes. But here you can see details about different data sets involved in ImageNet. But this website has all the information about ImageNet. But all we should try to understand from this from the second paragraph of the abstract is that when we pre-train the Vision Transformer on large amounts of data, okay, so we have now a pre-trained Vision Transformer, and then we perform transfer learning on some other benchmark tasks on smaller data set like ImageNet. I assume this is like 1K, ImageNet 1K, meaning 1K classes, or CIFAR 100 or VTab, etc. We'll see what these benchmarks are. The performance is better, and it's better than the state-of-the-art CNNs, and you require only fewer computational resources to train. So this is surprising, right? Basically, just a pure transformer architecture in the absence of convolution operation, performing really well on certain image tasks on some standard image datasets, and that too outperforming some state-of-the-art. So this is the value proposition of the paper. Now that we understand what this paper is trying to do using transformer architecture for image classification task or some other image recognition tasks, let's see how the paper implemented it. Now moving on to introduction section. For any paper, introduction forms, it sets the context. It says why this paper is relevant, what are the things that people have tried to do in the past, what this paper is trying to do differently, and what are the results. So this entire paper's context will be set very nicely in the introduction section. So earlier I used to think that results was the most important section in papers, but that's really not the case. Results can be good, can be not so good, it can be incremental. All of that is fine, but if people don't understand why you are doing what you're doing, they will not understand the significance of your paper. So introduction section plays that role where it really sets the significance, historical significance, as well as the importance of what you have achieved on an absolute scale. All of that will be written. All of that should be clear in the introduction section. So let's move into introduction. Self-attention based architectures, particularly transformers, by Vaswani et al. So this is now the Attention is All You Need paper by Ashish Vaswani and others, have become the model of choice in NLP. That was clear by then. This paper, Attention is All You Need, came in 2017, and the Vision Transformer paper came out in 2020, 2021. So 3-4 years of gap was there. The dominant approach is to pre-train on a large text corpus and then fine-tune on smaller task-specific dataset. Now, this Devlin paper is the BERT paper, if I'm not wrong. Yeah, so I think they are referring to this paper, which came out, I think the paper came out in 2018, but maybe they would have had another version. This also, by the way, was from Google, the BERT paper. I think this paper has 100,000 or more citations. We can just check here. Yeah, 147,000 citations. I wish to sometime review this BERT paper also, because it was also a seminal paper which did some things better than the original GPT paper which came out before BERT. So this paper also showed that you can fine-tune on smaller task-specific dataset after pre-training. So this was possible because transformers are highly scalable. The size of the transformers at that time was 100 billion parameters or up to 100 billion parameters, and now it is much, much bigger. We can ask ChatGPT what is the biggest parameter model now. I'm pretty sure 450 billion was already there. Let's see which is the 405 billion known large models, 540 billion palm from Google AI. Okay, it looks like something around 540 billion is what is big right now. So with the models and datasets growing, there is still no sign of saturating performance. So basically they are praising the transformer architecture in this paragraph and primarily citing the Bird paper and attention is all you need paper. In computer vision, however, convolutional architectures remain dominant. Inspired by NLP successes, multiple works try combining CNN-like architectures with self-attention. So it was still not purely self-attention based models. Convolution was still part of the architecture, but some papers tried replacing convolution entirely. This Ramachandran and others, Wang et al. The latter models, while theoretically efficient, have not been scaled effectively on modern hardware accelerators due to the use of specialized attention patterns. So basically what this paragraph is saying is, although transformer architecture has been used implemented in a widespread scale in language related tasks, in computer vision that is not the case. Still most of the models are relying on purely convolution or a mix of convolution and attention. But some papers like these two papers have tried variants where convolutions were entirely replaced. So what this specialized attention pattern means is instead of every patch in an image, so we are yet to see what an image patch is. So this idea we'll come back to once more, but image patch is simply you divide an image. Let's say you have an image like this, and let's say you want to convert this into 9 patches. You just divide the image column wise into 3 parts and row wise into 3 parts, and now you have 9 patches. Now just like tokens in a sentence where you have attention between one token and every token in the same sequence, in patches also this patch can attend to this patch can pay attention to this patch can pay attention to this, it can pay attention to itself, it can pay attention to this patch, the patches can pay attention to each other. So, but in this paper, what they did was, instead of computing attention across all tokens, they designed attention restricted to local neighborhoods, meaning they designed the attention such that meaning the Ramachandran and these two papers which are cited here, it restricted the attention to local neighborhood of tokens. Here tokens mean patches. So don't worry if you don't understand what these patches or if you can't visualize. I'm sure visualizing patch is not an issue, but if you can't visualize the attention process, etc. very nicely, just understand it is about how much importance should one token pay to another token. Let's say you have a sentence, the teacher who was teaching a difficult concept to students smiled. Now look at this sentence. In this sentence, you have teacher, you have students, and you have this action of smiling. If a language model cannot capture dependency between tokens that are far away, so what is token, by the way? Token is you divide your input sequence into words or subwords or characters. But for simplicity, you can assume token to be a word. So here, the token smiled and token students, although they are close to each other, they are not related to each other that much. On the other hand, smiled should pay more attention to teacher, because smiled and teacher is the person who is smiling in this case. So this is called long range dependency. So when we construct the attention mechanism, if you want to learn more about attention mechanism, I will put some reference videos in the description. But basically attention mechanism creates something called as attention scores, which can be later converted to attention weights, which tells the model that, oh, smiled as a word should pay 80% attention to teacher, 2% to who 1% to was, 1% to teaching, 0.5% to difficult, maybe 0.3% to students, etc. Like that, you can say that the word smiled should pay X percentage of attention to each word in the same sequence. So this is called as self-attention. Just like the self-attention in language, you can also construct attention between tokens in an image. And in image, what is the token? The token is a patch. What is a patch? Patch is when you divide an image into subsections. So you can say this patch, which consists of the head of the cat. Let's say head of the cat is here. Let's say hands of the cat. The front arms are here. Body is here. Back arms are here and tail is here. Then this patch should maybe pay more attention to this patch, and then this patch and this patch. And this patch, here there is no cat, here there is no cat, here there is no cat, here there is no cat. So maybe when we are training a model to classify images using transformer architecture, these patches also should pay self-attention. And when you restrict the tokens to only local neighborhoods, what does it mean? When the attention is constructed only between tokens that are geometrically close to each other, or only between patches that are geometrically close to each other, the model will fail to learn long-range spatial dependency. So although these two papers introduce the idea of attention without convolution for images, they were using specialized attention pattern, and because of that reason, they could not do large scale image recognition. So until the point where this vision transformer paper came into picture, classic ResNet, residual neural network like architecture, it was still the state of the art. It's amazing, right? So that is what this paper was trying to overcome. Like, it wanted to become the new state of the art. Now here, of course, you might feel like reading this paper, because there is one citation here, there is another paper. So truly, to understand the entire historical context of this paper, you might want to read the other papers also. But then if you do that, your journey will look something like this. Let's say this is your current paper. You will jump to some paper over here. Then you will jump to some 3 other papers. So you will always jump back in time, because always you're in current paper, you are citing the past papers. In those papers, you are citing the papers even from the past. So you will have a never-ending journey if you want to read every single paper. So of course, there are some knowledge gaps here. We still haven't gone into the details of what exactly the architecture of these two look like. But in 2 sentences, we can try to understand that they applied attention without convolution, but those attention patterns were specialized because you were paying attention to only self-attention was only between patches that were local. And because of that, it could not achieve the state-of-the-art results. That much you can understand. Now let's move into the next paragraph. Inspired by the transformer scaling success in NLP, we experiment with applying a standard transformer directly to images with fewest possible modifications. So you don't change transformer architecture that much. To do so, we split an image into patches. So this, I already showed you what this means, and provide the sequence of linear embeddings of these patches into a transformer as an input. So basically, we convert patches into linear embeddings, which are vectors. I'll show you this in a much more pictorial way. So you divide image into patches. Patches are converted into vector embeddings or linear embeddings, and those embeddings are fed into transformers. Similarly, in language, you split sentence into tokens. Tokens are converted into token embeddings, and those embeddings are fed into transformer. Image patches are treated in the same way as tokens or words in an NLP, just what I said. We trained the model on image classification in supervised fashion. So basically, this vision transformer paper, it is a supervised learning task where you are trying to perform image classification. Of course, ideally, we want an image model to be able to perform many more things, not just classification, but this is a good start. When trained on mid-sized datasets such as ImageNet without strong regularization, these models yield modest accuracies of a few percentage points below ResNets of comparable size. So what does this mean? It means when you are training vision transformer on smaller datasets without strong overfitting prevention techniques, without strong regularization techniques, the models do not perform, the vision transformer models do not perform as good as the state of the art ResNet models. And that is because the convolution operation has properties like translation invariance or locality. So translation invariance or equivariance, you can call it as either. Those are properties of convolution operations where if you have a filter, the filter can detect features in an image irrespective of where those features are present. So it doesn't matter if you have a circular feature at the top left or bottom right, as long as you have a filter which is designed, let's say the numbers inside this filter is such that when the filter acts on the image at regions where there is circular features, the resulting output will have, let's say, bright spots wherever there is circles and dark areas wherever there are no circles. Then it doesn't matter whether you have circle at the top left or bottom right. The CNN filter will, or convolution filter will definitely identify both. In transformer, however, detection of features is not through convolution operation. It's rather by dividing into patches, and patches are converted into tokens. So you have no idea when you divide the image into patches, these features are split across 4 different patches, or whether these circular shapes are part of just one patch. So you have no idea what happens to this patch by the time you are splitting it for feeding into a transformer. And transformer does not have this luxury of convolution operation to identify these features, irrespective of identifying these shapes or geometric features, irrespective of where it is present. And because of that, when you are training the transformer on a smaller amount of data, it does not perform as good as it would have performed on a larger amount of data. That is what this sentence is saying. However, the picture changes if the models are trained on larger data sets with 14 to 300 million images. We find that large scale training trumps inductive bias. What does that mean? Large scale training overcomes the inductive bias. So these things are called inductive biases: translation, equivariance, and locality, which are features of convolution. They are also called as inductive biases, which are inherently a property of CNN. It doesn't matter when you have a large data set. The large scale training trumps or wins over inductive bias. Our vision transformer attains excellent results when pre-trained at sufficient scale and transferred to tasks with fewer data points. So if we have vision transformer which is trained on big enough data set, let's say for classification, you can perform transfer learning of that pre-trained model for other tasks later. When pre-trained on public ImageNet 21K dataset. So ImageNet 21K is different from the ImageNet mentioned over here. So here it said if you are just training on mid-sized ImageNet dataset. So here mid-size means ImageNet 1K, I think. And here when they say ImageNet 21K, it's a 21 class classification or the in-house JFT 300 dataset. Now let's see what this dataset is. We can simply take a screenshot and ask ChatGPT, explain these 2 datasets, maybe in 2 to 3 sentences. I don't want a big paragraph response. I'm pretty sure ImageNet 21K is like probably million data points and 21K classes. JFT I haven't used personally, so I'm just curious to know what is JFT. So ImageNet 21K has 14 million and 21,000 category. JFT 300 million is proprietary Google dataset with roughly 300 million labeled images and 375 million labels. Wow, amazing. So that is what they meant by saying 14 million to 300 million. So 300 million is JFT, 14 million is ImageNet. I also want to know what kind of images are there in JFT, because ImageNet we know. What kind of images are there in JFT? Massive weekly labeled web scale image dataset created internally at Google, collected from the web, covering enormous diversity of everyday scenes. Okay, I guess it's kind of similar to ImageNet. ImageNet has animals, flowers, other objects, etc. So if such big data sets are used for training, then Vision Transformer approaches or beats state-of-the-art on multiple image recognition benchmarks. In particular, the best model reaches accuracy of 88.55% on ImageNet, 90.72% on ImageNet Real, 94.55 on CIFAR 100, 77.63 on VTab suite of 19 tasks. So here in the abstract, they had mentioned those three benchmarks: ImageNet, CIFAR 100, and VTab. We will come to that section to know what these data sets are about or what these benchmarks are about in detail. But the takeaway from the introduction section is that if you are training a vision transformer on big data sets with 14 to 300 million images like ImageNet or JFT dataset, you can exceed the benchmarks set by residual ResNet or residual neural networks. That's the takeaway from introduction section. One more important point from the introduction section is there were models which with pure attention without any use of convolution, it was there, but they were using specialized attention patterns. Here on the other hand, you divide image into patches. Patches are converted to embeddings. Embeddings are fed into transformers. That is how vision transformer works. Now let's look at some of the related work. So this you can consider to be an extension of introduction section. Usually if you are just writing one introduction section, there will be related work, mention of related work. Okay. Transformers were proposed by Vaswani et al. For machine translation and have since become the state-of-the-art method in NLP. Large transformer-based models are often pre-trained on large corpora and then fine-tuned for task at hand. BERT, which is the 2019 paper, amazingly written paper, uses a denoising self-supervised pre-training task, while GPT uses language modeling as its pre-training task. What does this mean? So BERT was basically using something called as masked language modeling. So if they had a sentence, they would tokenize it, and then some tokens they will randomly mask by using a mask token. So for example, mask token could look like this, right? And then the model will be asked to predict what this mask token is based on context from left hand side and right hand side. So left hand side meaning every tokens before the mask, right hand side means every tokens after the mask. So basically to make the prediction, the full context is available. So this is what was done in BERT model, and sometimes 80% of the times it was mask token, 15 or 10% of the times it was a random token, and another 10% of the times it was the same token. Basically, the mask, it was trying to predict what was corresponding to mask, but there was no mask token explicitly mentioned. Instead, it was like, for example, let's say I have a sentence like the cat sat on the mat. You know that this is a correct sentence. But if the sentence was something like the cat sat on the, let's say something like air, something like this. You don't sit on air. So here you know that this is the token where you are supposed to make correction in the sentence. So when you are training, if you put mask here, if you put mask here or mask anywhere else in the sentence, because you have good amount of training data, the model might learn to predict that this mask is supposed to be matte. But when you have an actual testing of the model, you don't have this mask. You don't know where the mistake is. The model should learn where the mistake is without having the presence of this mask token, which is why 80% of the times they use mask tokens as such. 10 or 15% of the times, I don't know the exact number, they used a random token, and another 10% of the times they did not replace the token. So in the input data, so if in the input data this was matte, they kept it as such. Okay, so this is how they did the masked language modeling in BERT. And while GPT line of work uses language modeling as its pre-training task. What does that mean? Language modeling simply means you don't expose the upcoming tokens to GPT. So GPT is asked to predict the next word. So the cat sat on the. So then GPT will be asked to predict mat. But before that, if GPT has access to the rest of the words GPT will not see, it will be asked to predict cat. Then the and cat it will have access to, it will be asked to predict sat. So it's not bidirectional. GPT has the context until the token that you are supposed to predict. So if you are supposed to predict token number 3, it has access to token number 1 and 2. It does not have access to tokens 3, 4 and 5. On the other hand, in BERT, if it's supposed to predict token number 3, it has access to token 1, token 2, token 4, 5, 6, right? So that was the difference between BERT and GPT. Although it's not completely relevant to entirely understand for the purpose of this paper, it's okay. So this is what it is called, causal language modeling or autoregressive modeling. Basically, the model is supposed to predict the next word. So naive application of self-attention to images would require that each pixels attend to every other pixel. So naive application means what is the most basic element of an image? The most basic element is pixels. So you could do something like you consider pixel as a token and then make sure that every pixel is attending to every other pixel. But then that's not a very smart thing to do, because if you have, let's say, 100 pixels total, 10 by 10 image, then every pixel has 100 pixels to attend. Pixel number 1 will have to attend to pixel number 1 itself, then to pixel number 2, then to 3, then to 4, etc. up to pixel 100. Similarly, pixel 2 will have to attend to pixel number 1, pixel number 2, pixel number 3, etc. So the attention weights matrix will be 100. So if you have 100 pixels, it will be 100 by 100. 10 raised to 4, that many numbers. So quadratic cost, that's what they mean by quadratic cost. If you have 100 pixels, the number of attention weights will be square of that, 100 square. So this is not very realistic thing to do for scaling. Thus, to apply transformers in the context of image processing, several approximations have been tried in the past. Parmar et al. Applied self-attention only in local neighborhoods for each query pixel instead of globally. So they used pixels, but then applied self-attention only to neighboring pixels. So I don't think they did patching. They used pixels directly, but only looked at, for constructing attention scores, only looked at the local neighborhood. Such local multi-head dot product self-attention blocks can completely replace convolutions. So this Ramachandran paper was also, and Zhao paper, I think both of these papers were mentioned over here. Not Zhao, Wang. Okay, Ramachandran paper, same paper which was mentioned here, where they constructed a specialized attention pattern. So it can entirely replace convolution, which was already discussed in the introduction section earlier. In a different line of work, sparse transformers employ scalable approximations to global self-attention in order to be applicable to images. An alternate way to, so I'll just give you a summary of what this paragraph is saying. Basically, what this paragraph is saying is researchers up until that point was paying attention only to local regions. Or sometimes they use something called sparse connections, or sometimes they divided image into blocks. The basic issue was these methods were much more complex to implement because they were computationally not very efficient. So that's the final takeaway here. So here, in fact, they are referring to a lot of papers. So if you truly want to understand the essence of this full paragraph, not essence, if you want to truly understand this paragraph deeply, you will have to look at what each of these paper has done. But the takeaway from this paragraph is that what people have tried before was interesting. People tried to implement things in the without convolution operation, but they had issues when it came to implementation in an efficient way. Okay. And then interestingly, in this paragraph, they mention about one work which was very close to what these guys are doing. Most related to ours is the model of Cordonier et al. I don't know how to pronounce this name in the best way, which extract patches of size 2 by 2 from the input image. So basically 4 pixels, each patch is 2 by 2, and applies full self-attention on top. So basically the image is divided into patches of 2 by 2 and entire self-attention is applied. This model is very similar to vision transformer because that is exactly what we are going to discuss in the paper. But our work goes further to demonstrate that large-scale pre-training makes vanilla transformers competitive with the state-of-the-art CNNs. So if you really want to show that transformer architecture can be used for processing images, you have to be able to show that it is better than state-of-the-art SOTA models, right? And when you are looking at patches of size 2 by 2, you will have a lot of patches in an image because each patch is only 4 pixels. So if you have 400 pixels in an image 20 by 20, you will have 100 patches. So this applies to only small resolution images. So what was the issue with the previous work done by these guys, Cordonier et al.? The issue was the patch size was too small, and because of that, it applied only to low resolution images. That was the first issue. Second issue was that they could not show that that model was, as good as the state of the art. There has been a lot of interest in combining CNNs with forms of self-attention. So again, they are now discussing previous work in this particular paragraph, previous works in the paragraph. There has been a lot of interest in combining CNNs with forms of self-attention by augmenting feature maps for image classification, or by processing the output of a CNN using self-attention. So basically, you use a CNN to extract features, and whatever you get as a feature map, that you feed into the self-attention instead of feeding the pixel values themselves directly. And this was used for object detection, bounding box, basically drawing bounding boxes, video processing, image classification, unsupervised object discovery, or unified text vision tasks. Another recent model is Image GPT or iGPT, which applies transformers to image pixels after reducing image resolution and color space. So basically you have a bunch of image pixels, but you compress it significantly to reduce the resolution. And I guess when they say reducing color space, they mean, I guess they are simply removing some color channels. So instead of having multiple channels, maybe one channel, something like that. The model is trained in an unsupervised fashion as a generative model. So maybe they are asking to recreate some patches instead of performing classification, and the resulting representation can be then fine-tuned or probed linearly for classification performance, achieving maximal accuracy of 72% on ImageNet. So what this paper, this Image GPT paper tried was, we can also ask ChatGPT to give a better paraphrasing of this paragraph. Let's say simplify this. So what we understand by reading this paragraph is, in Image GPT, you compress the image spatially as well as channel wise. And then after you do that, you pass it through you pass it through transformer, but you are not doing directly image classification. You are doing a generative task. What does it mean by generative task? I guess it's generation of patches. Let's see if that is indeed what it means. So my GPT is slowing down. Let's come back once GPT has given the response. So GPT says, in the context of Image GPT, iGPT, it could be predicting the next pixel, or it could be predicting patches. The model is trained to predict the next pixel, similar to how GPT predicts next word. This means it learns the underlying distribution so that it can generate new realistic looking images. All right. So it's not necessarily patches. It could be pixels as well. Now, the next paragraph is about what is so special about this paper. Our work adds to the increasing collection of papers that explore image recognition at larger scales than the standard ImageNet dataset. What is standard ImageNet dataset? The 1K dataset. The use of additional data sources allows to achieve, let me just pick the highlighter, allows to achieve state-of-the-art results on standard benchmarks. Study how CNN performance scales with data size, and perform empirical exploration of CNN transfer learning from large-scale datasets such as ImageNet 21K and JFT 300 million. So basically, it's saying what we already understood from the earlier paragraphs. So we focus on these two later datasets, so these two datasets as well, but train transformers instead of ResNet based models used in prior works. So basically in this paper, we'll be training ResNet based models on these two datasets primarily to see how its performance compared to benchmark looks like. What are the benchmarks? It was mentioned in the abstract, these three benchmarks, image recognition benchmarks, and we'll see how the performance look like. Okay. Now, this is the figure 1 of the paper. Figure 1 is the vision transformer architecture. Although this figure may look intimidating, we can just go through it slowly by taking enough time. So let's look at what happens to the image first. The image, this is the image, okay? And it is split into patches. So how many patches? Here there are 9 patches. So image is divided into 3 by 3 patches, 3 along width and 3 along height. Then after converting the image into patches, the patches are put linearly. So you are basically flattening the image here, okay? So the kind of the spatial relationship between the patches is gone. And then the image is converted into token embeddings. So these are token embeddings. So, or rather patch embedding. So patch is tokenized and those tokens have embeddings. Embeddings meaning vectors. So for this patch, this is the vector representation. For this patch, this is the vector representation. For this patch, this is the vector representation, and so on. Now there is one more thing for you to notice. You have something called as position embedding. That is the first thing you have to notice. So you are adding position information. So this one means this is the patch number 1. This is patch number 2, patch number 3. So you're adding position embedding to your input embedding. This is also done in GPT or in transformer for text. Depending on the token's position, you have a position embedding vector. It may be a learned vector or it could be based on formula, predetermined formula. And that position embedding you add to the input embedding. Both will have same dimension. But interestingly, you can see one more thing here. What is this? So this is called as the classification token or class embedding. So this is the extra token that is added at the very beginning, where the position corresponding to that is 0. So position 0 is the CLS or class token. And finally, after this whole embedding passes through the transformer encoder. So transformer encoder is what? It looks like BERT, right? So if it was transformer encoder, it will look like BERT. If it is decoder, it will look like GPT. Pretty much the same. This left-hand side, basically, which left-hand side? This one. So this looks like BERT. This looks like GPT. Because in GPT, you have masked multi-head attention. You are masking the model from seeing the future tokens. In BERT, you don't have to do that. So here the model is similar to BERT. So you have a transformer encoder and then you have a multi-layer perceptron classification head. This classification head performs classification just using one token. Which one is that? The classification token. So what the vision transformer does is it constructs self-attention using the tokens corresponding to patches, plus at the beginning, you also have a class token embedded. So this is an extra token added. So if you now you have 10 tokens, right? 0 to 10 in this image. According to this image, you have 9 corresponding to the image and 1 corresponding to the class embedding. So now you have 10 tokens. So you will have to construct the attention scores corresponding to those 10 tokens as keys, as queries, and those 10 tokens themselves as values. So 10 by 10, you will have 100 attention weights. And using those attention weights, you can get 10 better context vectors. Now, 10 context vectors will correspond to 10 of these input embeddings. And now only one of those context vector will be used in the multi-layer perceptron for performing classification, which is the context vector corresponding to this guy. So each of these input embeddings will be converted into a better context vector through the transformer encoder. And then the representation of the representation in the context vector corresponding to token number 0 will be used for performing classification. And the predicted class will be whatever classes are there in your input data set. So if it's a 21K class classification, you will expect that many classes. And then you can construct a loss using softmax or basically you have softmax probability distribution and class construct cross entropy loss. Now the transformer will look like BERT. So just look at this. You have multi-head attention. Okay. You have multi-layer perceptron. Those are the two biggest things of the transformer encoder. There is layer normalization before. This is query key value. So you are converting your input token into query key value. Multi-head attention then construct the attention weights using query and key. Then attention weighted value is the final context vectors. So when I say these things, I'm sure if you are a complete beginner who have not spent enough time on transformers, this will not be making too much sense to you. So I will link the lectures which you can watch, which are much shorter in length for you to understand how exactly a transformer architecture works. But I'm skipping some concepts here, I know. But if I also have to teach transformer in the middle of vision transformer, it will be a whole another lecture, and this will become maybe 20 hours in length. I don't want to do that. So, but just understand that there is multi-head attention and multi-layer perceptron. Before that, there is layer normalization and there are residual connections. So this is a residual connection. This is a residual connection. Okay. You can see the exact same thing here. This is exactly same as this. All right. And what are these embedded patches? Embedded patches are your patches from images, which are 9 plus 1 for the classification token. Okay. Just read this title, the figure description also. We split the image into fixed patch sizes, then linearly embed each of them. We know that. Add position embedding. We know that. Feed the resulting sequence of vectors to a standard transformer encoder. We know that. In order to perform classification, we use the standard approach of adding extra learnable classification token to the sequence. We just saw that. Okay. Now, method. In model design, we follow the original transformer as close as possible. An advantage of this intentionally simple step is that scalable NLP transformer architectures and their efficient implementation can be almost used out of the box. But basically what they're saying is they are using pretty much the same transformer architecture as that of the attention is all you need paper. Now let's come to some details about the vision transformer. We saw the details in the figures, but just let's see how in terms of vectors and matrices, in terms of dimensions, how this looks like. An overview of the model is depicted in figure 1. We just saw that figure 1 above. The standard transformer receives as input a 1D sequence of token embeddings. What are those? Those are the embeddings corresponding to your patches. To handle 2D images, we reshape the image into sequence of flattened 2D patches. Now let's see what this means. X belongs to something consisting of real numbers of dimensionality h by w by c. H is the height of the image, W is the width of the image, and C is what? C is number of channels, RGB. So this could be 224 by 224 by 3, for example. So this H by W by C is converted into a sequence of flattened 2D patches. Now, how does that work? So if your resolution of the patch is P by P, so let's say your image is H is the height, W is the width, okay? And let's say your patch dimension is P by P. How many patches you will have? You will have H by P along the height multiplied by W by P along the width. So overall, the total number of patches will be HW by P square. This is the number of patches equal to N. So that is what they say here is the resolution of each image patch, and N equal to HW by P square is the resulting number of patches. So you will have N patches, but in each patch, how many numbers do you have? Let's see. So in each patch like this, how many numbers do you have? In each patch, you have P square, of course, because the patch size is P by P pixels. But like that, how many channels do you have? You may have 3 channels if it's an RGB image, or C number of channels. So total you have P square multiplied by C. That many numbers associated with one patch. So P square C will be the dimensionality or the size of the numbers associated with one patch. So here what they are saying is the final representation of each 2D each patch into a flattened shape. So once the patches are flattened, you will have n patches where n equal to height width divided by p square. P is the patch size. Okay, you will have n patches, and each patch will have how many numbers? Each patch will have, one patch will have p square, but then you have c channels, so p square times c. So n times p square c. This will be the sequence of flattened 2D patches. Why do we say flattened 2D patch? Because this is the flattened 2D patch. So if number of channels is 1, let's say this was a black and white image, what will this look like? This will look like each of them will be of p square dimensionality, p by p, and like that you have n number of patches. So n times p square. Here it is p square multiplied by 1, but if you have c channels, it will be p square multiplied by c. Okay. Okay, so this is the resulting number, which also serves as effective input sequence length for the transformer. The transformer uses a constant latent vector size d through all of its layers. So we flatten the patches and map it to d dimensions with a trainable linear projection. What does this mean? This means we are converting now the image patches into some vectors. So let me just delete some of these things. We have to convert this into a vector, this into a vector, this into a vector, this into a vector. Each vector should be of dimensions d. And that is done using this linear projection, which is a neural network. So it converts these image patches into a vector of dimension d. So the dimensionality of the patches which is being fed into the transformer is d. In GPT-2 small model, the dimensionality was 768. In GPT-3, it was 12,288 and so on, the dimensionality of the token. Now, in BERT also, they had a classification token. So similar to BERT's class token, we prepend. So we are prepending, prepending meaning not appending. Appending is at the end, prepending is at the beginning. We prepend a learnable embedding to the sequence of embedded patches. So how many sequence of embedded patches you have? You have n number of patches. And before that, you are adding the class token. And so that now you have n plus 1 tokens. And whose state at the output of the transformer encoder. So what does this ZL0 mean? So Z is the context vector, which is the vector of dimensions d, corresponding to your token number 0. Token number 0 is the class token. And what does this L mean? L means after your Lth transformer layer. So here you have, or transformer block, you will have L number of transformer block, Lx. Lx means this transformer encoder is repeating L number of times. In GPT-2, they had 12 of these, if I remember correctly. In GPT-3, they had 96 of this. Okay. So after the Lth layer, the representation of the class token will be ZL0, 0 for the token number 0. Like that, there are 0 plus another n number of tokens. So this ZL0 token will serve as the image representation. Now you might have a question, how come this token is able to represent the entire image? What about the rest of the tokens? So the attention mechanism does this. So if you remember, for predicting the next word, okay, for predicting the next word, you were using the context vector associated with the very last token. So if the input is the cat sat on the, okay, let's say this is the sentence you feed to GPT, and GPT, you know, it predicts the next word. To predict the next word, the context vector corresponding to this guy is utilized. So somehow you are expecting the context vector corresponding to embed the information in the entire sentence, or in the entire set of tokens that was there before. And just like that here, what we are doing is you are relying on instead of the last token, you are relying on the 0th token or 0th patch, which is the class token, to embed the information corresponding to the entire image. And then you rely on this 0th token to make the prediction on what is the class associated with this image. Okay, so it's kind of similar to GPT in the sense that instead of relying on the last token, here you rely on the 0th token. Okay. Both during pre-training and fine-tuning, a classification head is attached to ZL0. Do you see what this means? It means the multi-layer perceptron which performs the classification is attached to the context vector associated with 0th token. Where do you see that? In the figure, this one. So this classification head, MLP classification head, is attached to the 0th token. Okay. And the classification head is implemented by an MLP, by a MLP with one hidden layer at pre-training and by a single linear layer at fine-tuning. We'll see what this means. One hidden layer at pre-training and only single linear layer during fine-tuning. During pre-training, it will look something like this. You have incoming token of D dimension. So you'll have D nodes in the initial layer, maybe 4x multiplied by D, that many in the next layer. And here, if it is a 21K classification, you will have 21K number of nodes. So here D nodes, here 4D number of nodes, and here 21K nodes. So you are converting this into 21K, and then you can convert into softmax probability distribution across 21K numbers. So this is what is being done in the multi-layer perceptron. So this is the MLP in pre-training, and during fine-tuning, they said a single layer at the fine-tuning time. Maybe what they mean is at fine-tuning, they probably don't have this. We'll see what that means. They probably just have this, depending on the number of classes. So if it's a 1000 class classification, instead of 21K nodes, it will be 1000K nodes. But here it will be D, the dimensionality of the input embedding. Okay. Then position embeddings are added to patch embeddings to retain positional information. We use standard learnable 1D position embedding. So we don't just add saying position number is 0, position number is 1. We don't do that. Instead, we add something like a learnable position embedding, since we have not observed significant performance gains from using more advanced 2D aware position embeddings. So basically, it doesn't matter if you are explicitly adding 2D aware position embeddings. What do you mean by 2D aware? It means you know that, for example, this patch number 1,1 is closer to patch number 1,2 and 2,1 rather than 3,3. So that is, so if you add embeddings, position embeddings such that this factor is in part of the embedding, then it means it's position aware. But if it's a learnable embedding will learn whatever it can learn, right? You are not forcing it to learn something associated with the position. So they saw that adding more advanced 2D aware position embedding versus learnable 1D position embedding did not make much difference. They also have a figure in the appendix, which I'll show you, which shows that it doesn't matter which of these embeddings you add. The transformer encoder consists of alternating layers of multi-head self-attention, MSA, and MLP. You saw that MSA is this. So sorry, MHA is this, MLP is this. It's alternating from this to this. And you have many such attention heads. Then layer normalization is applied before every block. So layer normalization you will see before MHA as well as before MLP, norm. Then you have residual connections. After every block, residual connections allows the transformer to reduce vanishing gradient issue while training. So these terms may not make sense to you if you don't have exposure before. But I hope once you go through the lecture video corresponding to the transformer architecture, which I will share with you, it will make much more sense. But this is basically the standard transformer architecture. The MLP contains two layers with JLU nonlinearity. JLU is similar to ReLU, except it's much more smooth. So you can see the JLU function over here. So this is JLU function. It's a smooth, continuous, differentiable function. ReLU, on the other hand, it's not differentiable at x equal to 0. So ReLU will look like a sharp function, okay? Rectified linear unit. Now JLU nonlinearity is the activation function used in the MLP. MLP contains two layers. Now here, this is some mathematical notation. I can also skip this because you already know what these things are, but maybe I can go through this once so that you will feel like you have an entire grip or proper grip on the paper. So let's go through these mathematical notations once properly. So here, let's look at the input. Your input vectors look like this. Z0, it's X class, comma, next token, like that. There are n patches. So there are n tokens, plus you are prepending the classification token, which is called as X class. But here you can see something, xp1e, x square pe, etc. So this is nothing but the linear transformation happening to your patches so that it's converted into a d-dimensional space. So let's look at the individual dimensions of these. xp has a dimension of what? It has a dimension of 1 by p square c, because as I mentioned, each patch has p square numbers, and then if there are c channels, p square multiplied by c. So if you are flattening a patch, it will be of dimension 1 by p square c. Now, if you are using a linear projection to convert this into d dimension, that should be a matrix whose first dimension is p square c and second dimension is d, so that when you multiply these two matrices of dimension 1 by p square c and p square c by d, you get something like 1 by d, correct? So the matrix, transformation matrix, which performs the embedding, which is denoted by E here, is of dimension p square c by d. And the dimensionality of these patches will be 1 by p square d. Now, the position embedding E position will have how many dimensions it will have, or how many items there will be? There will be n plus 1. It's not just n, because the number of positions that are there, including the classification token, is n plus 1. You have n patches plus the classification token. So this will be n plus 1 multiplied by d. If classification token was not there, this would be n times d. N being the dimensionality of number of patches, d being the dimensionality of the each individual vector. Okay. So essentially what this is saying is, you convert your tokens or you convert your patches. This mathematical expression is simply saying this much. You have patches, n number of patches. Each patches you are projecting into a vector of dimensions d. To each of those vectors, you are adding another vector of dimension d, which embeds the position information. But along with these n vectors, you also have a classification token prepended, which is this x class. And to that x class also, you are adding the position information or position embedding, which is corresponding to 0th position. Okay. Then in transformer architecture, the output that comes out of the Lth layer, because we said that there are capital L number of transformer blocks. So the output that comes out of the multi-head self-attention, MSA is multi-head self-attention, is, so what goes into the multi-head self-attention is what comes into the layer normalization from the previous layer, right? So let's go back to our image. So our image was this. So what goes into multi-head self-attention is what comes out of the layer normalization. And what comes into the layer normalization is whatever is coming from the previous, L minus 1th layer. So in the Lth layer, what is coming out is whatever output is coming from the L minus 1th layer. Here when I say layer, I mean L minus 1th transformer block, Lth transformer block. What is one transformer block? This entire gray color thing is one transformer block, this big thing. Okay. So after the embedded patches are fed into one transformer block, like that, L number of transformer blocks repeat in series. We'll see what the number L is once we see the different size vision transformers of different sizes. So what comes into a transformer block number L is whatever comes out of transformer block L minus 1. So that is what is written here. So layer normalization of the context vectors coming out from the L minus 1th transformer block produces an output. That output is layer normalization of ZL minus 1. Then that input goes into multi-head self-attention of the Lth layer. And then to that, we are adding the residual. What is residual? Residual is literally the input coming from the L minus 1 block. So the residual is nothing but whatever comes out of the previous layer all the way goes here and is added over here. So whatever is here goes all the way here and adds not here, not outside. It's added at the right after the multi-head attention. So that is what this plus is. So multi-head self-attention produces an output corresponding to whatever output comes out of the layer normalization. The input that goes into the layer normalization is the context vectors from the previous transformer block. Then after multi-head self-attention, there is addition of the residuals from the whatever is the output coming from the previous transformer block. Is that it? No. Now this input undergoes one more layer normalization, because we know that multi-head self-attention is followed by multi-layer perceptron, but before that there is layer normalization. So ZL prime undergoes layer normalization, and whatever output comes out of that goes through multi-layer perceptron. Then there is one more residual from the above figure. That one more residual is nothing but whatever is coming out of the whatever is this ZL prime. So ZL prime comes as the residual addition. And then this output ZL is the final output coming out of the Lth layer of the transformer block, or Lth transformer block. Now, if L equal to capital L, once L becomes capital L, you are passing through all the L number of transformer blocks, and then it goes through one more layer of layer normalization. So Y equal to layer normalization of ZL of 0. So here you are only performing layer normalization on the classification token. ZL0 means you're looking at the context vectors. Z is the context vectors produced from the Lth transformer block. That too, you're not looking at all tokens, you're only looking at 0th token. 0th token is the classification token. So this layer normalization is not visually represented in this figure yet, but you can imagine it to happen sometime before this MLP. So before MLP, there is one layer normalization that happens to the classification token. So that's it. Mathematically, it's very simple. And here you can see that small l runs from 1 to capital L. What this means is the number of transformer blocks is L, capital L. This is the number of transformer blocks. Okay. Now, inductive bias. We note that vision transformer has much less image specific inductive bias than CNNs. We know that because inductive bias, as we discussed, the locality and spatial invariance, or those features are classic features of convolution operation. In CNNs, locality, two-dimensional neighborhood structure, and translation invariance or equivariance are baked into each layer throughout the whole model. What do you mean by each layer? In convolutional neural network, you will have a bunch of layers. If you look at the ResNet, let's say ResNet model architecture, you will see bunch of layers one after the other. So this is the first convolution block, next convolution block. After each layer, the number of dimensions spatially reduces and the number of channels increases in the image. That is what usually happens in a convolutional neural network. So this translational equivariance, two-dimensional neighborhood structure, locality, these are features that are inherently baked into each layer of the CNN, because in every layer there is convolution operation. In vision transformer, only multi-layer perceptron are local and translationally equivariant, while self-attention layers are global. So what does this mean? So self-attention layer is global simply means self-attention attends to every single patches that are coming in. It does not matter if two patches are close to each other or not. It looks at every single patches that are coming in. Okay. So that is it. That is what it means by multi-layer, the vision transformers, multi-head self-attention, that part is global. The multi-layer perceptron, on the other hand, it is local and translationally equivariant. Let's see why that is the case. We can ask ChatGPT, why is MLP in the vision transformer local and shows translational equivariance. So my thinking is, it doesn't matter in which dimensions of the context vector your features are, whether it's in dimension number 2 and 3 or whether it's in dimension number 17 and 18, it doesn't matter. Those features will be taken into account when you are projecting into a higher dimensional space in MLP and then when you are projecting it back. But let's read what GPT has to say. So patch embeddings introduce spatial locality. In Vision Transformer, image is first divided into non-overlapping patches. We know that. Each patch becomes a single token, like a word. We know that. So within a patch, spatial information is already aggregated locally. The MLP only processes one token at a time, not mixing pixels. Okay, so what this means is the multi-layer perceptron is considering each tokens independently, meaning it considers each patches independently. So that means already whatever information is spatially available in one patch, only that information is available to MLP. So I guess that is what here in the context of this particular sentence, only MLP layers are local and translationally equivariant. So I guess translationally equivariant means it doesn't matter whether MLP is looking at certain features in a patch, whether the patch is in patch number 1 or whether that patch exists at position number 16. It doesn't matter because the multi-layer perceptron is having a look at every single patches separately. So, and because of that, it doesn't matter where the patch exists in the image position wise. I mean, slight difference will be there because you are adding position embedding, I guess. But overall, I don't think it makes much difference. So I think that's what they're trying to say. MLP acts independently on each patch token. Inside every transformer block, the MLP is applied separately to each token embedding. Makes sense because you have n+1 tokens in this case, classification token followed by n patches. So here all of them are, if MLP wanted, no, we are not talking about the final MLP yet. We are talking about the MLP in the transformer block. The MLP is looking at every single patches separately. That means same MLP weights are used for all patches, but it doesn't mix information between tokens. So it acts as local non-linearity. Translational equivariance, I think this is straightforward. It doesn't matter where the location of patches, you can still extract, MLP can still extract the same information. The two-dimensional neighborhood structure is used very sparingly. What does this mean? So because the Vision Transformer paper's big claim is that it's not using two-dimensional structure information, unlike CNNs. In CNNs, the convolution filters are inherently using two-dimensional information. The claim of Vision Transformer paper is that that is not being done, but there are two places where it is done. One is in the fact that you are cutting image into patches. When you are cutting into images into patches, and when those patches become tokens, inherently those tokens, the information contained in that token is belonging to that local patch. And at the time of fine tuning, so one place where this 2D structure is coming into picture is when in the very act of cutting image into 2D patches. The second place where this comes into picture is at fine tuning, which we haven't discussed yet in the paper. We will come to that. In fine tuning, this comes into picture where if you want to adjust the position embedding for images of a different resolution, let's say during training you used image of 224 by 224 pixel, but during fine tuning you are using image of let's say 520 by 520 pixel, something like that. Then you have to have position embedding for those new positions. And you know that position embeddings, as discussed earlier, are learned embeddings. They're learnable numbers. They are not predetermined. So how do you then use the position embeddings for this new image of a different resolution? We'll see how this is done. But those are the two places where two-dimensional information is being utilized in Vision Transformer. That is what is said in these two sentences. Other than that, position embeddings at initialization time carry no information about 2D positions of the patches, and all spatial relationship between patches have to be learned from scratch, meaning the position embedding vectors are not predetermined vectors. The numbers, the values inside those vectors are learned. Now, hybrid architecture. This green rectangle I only drew. It was not part of the paper, so please don't get confused. I just drew it because this paragraph I thought was important. So hybrid architecture is as an alternative to raw image patches, the input sequence can be formed from feature maps of a CNN. What does this mean? Instead of feeding the image directly into Vision Transformer, you can pass the image through a convolutional neural network and extract features and get feature map. How does the feature map look like? Feature map CNN. It will look something like this. It will be abstract. See, these are examples of feature maps corresponding to the handwritten digit 9. And you can also see the filters that resulted in these feature maps. There are 16 feature maps, and these are the filters that resulted in those feature maps. Here is another example of feature map. So all the time feature map need not be something that is concrete. Here you can see that these feature maps corresponding to first layer it's much more concrete. You can make out that it's like a cat. But in the later layers, you don't know what the feature maps are meaning, right? So you could embed the information in the image into an abstract feature map using convolution and then feed that feature map into the transformer. So that is called as hybrid model. In this hybrid model, the patch embedding projection E, so patch is embedded into feature map E, is applied to patches extracted from CNN feature map. So the embedding is not performed on the image patches directly. It is applied to patches extracted from CNN feature map, meaning it is applied to feature maps that look like something like this. So instead of dividing the original cat image into patches, you divide these feature maps into patches and then embed those. As a special case, the patches can have a spatial size 1 by 1. So patches could be just 1 pixels instead of 16 by 16 pixels or something, which means that the input sequence is obtained by simply flattening spatial dimensions of the feature map and projecting to the transformer dimension. So if transformer dimension is D, you are simply projecting your feature map into that particular dimensionality D. The classification, input embedding, and position embeddings are as described above. Basically, you have classification token, extra token prepended, position embedding, exactly like a learnable embedding, it's added. All right, this is a hybrid architecture. Then fine tuning and higher resolution. So this paragraph explains how, if the input image resolution is different than what it was used during training, how do you add position embedding? Typically, we pre-train vision transformer on large data sets and fine-tune to smaller downstream tasks, meaning smaller tasks later after pre-training. For this, we remove the pre-trained prediction head. So what is the prediction head? The MLP, this head in this image. We can remove this MLP head. Where is our paragraph? We remove the pre-trained prediction head and attach 0 initialized D by K feed forward layer. So this D by K we already discussed. You remember here? Here we discussed we will have D multiplied by, if there are K classes, D by K. So here 21K and the K that I am discussing right now are different. 21K is 21,000 classes, but here the K value of K itself is 21,000. Okay. So you will have the D-dimensional context vector corresponding to the classification token projected onto a K-dimensional space where K is the number of classes using just a feed-forward layer. So K is the downstream number of classes. It is often beneficial to fine-tune at a higher resolution than pre-training. When feeding images of higher resolution, we keep the patch size the same, right? Which means if image resolution is high and patch size remains the same, obviously number of patches will increase, right? Because number of patches is equal to HW by P square. So if P remains the same, but H and W changes, N will change. If N changes, the position embedding vectors need to do something. It has to change, which results in a larger effective sequence length. The vision transformer can handle arbitrary sequence lengths. However, the pre-trained position embeddings may no longer be meaningful. The pre-trained position embeddings earlier was for N positions, but now the value of N changed because H and W changed. Now the earlier position embeddings will not be meaningful. We therefore perform 2D interpolation of the pre-trained position embeddings according to their location in the original image. So basically, the pre-trained position embeddings we use not directly, but by 2D interpolation. What we can do is, let's take a quick screenshot of this and ask GPT to give us an example of this 2D interpolation for our better understanding. Explain this 2D interpolation in vision transformer. So now this is the response in vision transformers, position embedding when we are fine tuning to images of different resolution. This is what we do, what vision transformer does. So in pre-training, if the image size is 224 by 224 and if each patch is 16 by 16, that means you have total 14 by 14 patches, which is totally 196 patches. So you should have position embedding for 196 plus 1 because you have the position embedding for the classification token also. But now if you suddenly have a higher resolution image in fine tuning like 384, so 384 divided by 16 is the patch size, which is not changing. Now you have 24 by 24 patches, so you have that many, 576 patches. So what is done is in vision transformer, 2D interpolation is as follows according to GPT. And in my opinion, it might be better to get a numerical example. So let's say give a numerical example of 2D interpolation. So that way we can see how already existing position embeddings are utilized for creating new position embeddings for a higher resolution image with more number of patches while doing fine tuning. So I have asked for a even simpler example because we just want to deal with maybe 4 numbers and produce an interpolation as a result. So here the example is 0, 0, embedding value is 1 at position 0, 1. So patch number 1, which is on the right hand side top, its embedding value is 2 and 3 and 4. So let's say you have 4 patches and you produced position embeddings and the value of those embeddings are 1, 2, 3, 4 corresponding to 4 patches. In reality, it will be of course different. Now, if you are interpolating along the rows, so in 2D, you should be interpolating along the rows as well as along the columns. So along the rows, if you want to convert this 2 by 2 grid into a 3 by 3 grid, so how would that look like? Something that resembles this. So let's say I have four patches and position embedding of these patches are such that this is 1, this is 2, this is 3 and this is 4. So now this is 2 by 2. So totally there are 4 position embeddings, and let's say we want to expand this to 9 embeddings. The corner values would remain 1, 2, 3, 4. In between, this could be 1.5. You are interpolating. This could be 3.5. This could be 2. This could be again 4.5, 5. This will be 2.5, and this will be 3. So here, essentially, you are interpolating along the column as well as along the rows to produce these embeddings. So now these are position embeddings. These are not the values of patches themselves. Okay. The values of patches are different. These are the position embeddings corresponding to 4 patches in a 2 by 2 patch setting. These are the position embeddings corresponding to 9 patches in a 3 by 3 setting. And these patch position embeddings we will add on top of the input embeddings where each patch is represented as a vector of d dimensions. Alright, so I hope this part makes it clear. Alright, so now let's get back to the paper. We left off over here. Note that this resolution adjustment and patch extraction are the only points at which an inductive bias about the 2D structure is manually injected into vision transformer. So when we are creating patches, that is one part where actually vision transformer is considering things in 2D, because when you create patches, you are dividing it based on a 2D grid. The second part where the vision transformer looks at things from a 2D perspective is creating the new position embeddings for patches if your image resolution is higher for fine tuning. Okay, so we have covered a good chunk of the paper, but we still have a long way to go. So one issue that you might face while reading papers is that you might get physically tired, you can get mentally saturated, which is very, very likely to happen. And if you really look at the paper, so far we have covered maybe 3 pages. That's it, right? This first page, second page, and third page. Second, third, and fourth. Yeah, we are almost at the fourth page. And this is actually a 22-page paper. We don't have to go through all the pages in so much detail, and the results section is actually easier than the methodology and the introduction section because it's mostly tables that display the results. We don't have to dissect it so much, but it is very likely that you might feel tired. So what my opinion is, when you are reading the paper, do take long breaks. Do not expect you to read the paper in one sitting. It will definitely make you tired and you will not understand what's happening in the second half of the paper if you have finished first half already. So at this point, for example, in this lecture, if you really want to take a break and come back later, you should, of course, feel free to do so. Otherwise, it's very difficult to finish a paper. You will feel cramped. Your back might hurt. You are sitting for a long time. Even while recording this video, I felt the same effect. Like, I realized that the amount of energy I have to expend because I'm continuously talking is much more than when I was just reading the paper myself. So it was much easier to read the paper myself than record this. So even I am breaking the video into chunks and recording it after taking breaks. Sometimes, for example, this part of the recording I'm doing the next day compared to the previous part so far, the part so far. So I think same thing applies for somebody who is reading a paper, right? So I hope you don't take it too hard on yourself if you are getting tired or if you are getting mentally saturated. All right. So I just wanted to say that just to motivate you in case you are feeling tired, which is very likely. So now let's go forward with the next section, which is experiment section, which is described in the paper. So here is where we actually see how these different vision transformer models are constructed. So they have base, they have big, and one more, base, large, and huge. So those are the three models. So we'll see what kind of experiments they conducted and what kind of benchmarks that they compared these experiments against. We evaluate the representation learning capabilities of ResNet, vision transformer, and hybrid. So here hybrid means the model where you don't use images directly, you pass the image through CNN to produce features and then convert feature matrix to patches and use that patch. And feature is basically this. We already discussed this, right? So that's the hybrid. So in hybrid, you are not entirely getting rid of CNN. You are sort of like trying to get the best of both worlds. To understand the data requirements of each model, we pre-train on datasets of varying size and evaluate many benchmark tasks. When considering the computation cost of pre-training the model, Vision Transformer performs favorably. This is interesting to know. Attaining the state of the art on most recognition task benchmarks at a lower pre-training cost. So how is this pre-training cost estimated? We will also see that. Lastly, we perform a small experiment using self-supervision and show that self-supervised vision transformers hold promise for the future. This is very important because in the actual transformer for language, they did not manually label the dataset. There, the self-supervision was from the fact that you take text-based data from internet and you try to predict the next word given you have a set of words, right? And this you do by moving your context window from left to right. So let's see if Vision Transformer can also do sort of self-supervision. And if this is something that it can do successfully, it's very good. That way you can train on large amount of internet data set. So now the experimental setup, first we discuss about data sets. So for exploring model scalability, we use, initially we use the ImageNet 1K class dataset, and we know that this is a small data. So ImageNet 1K we are calling as ImageNet in this paper, and it has only 1.3 million images. On the other hand, the bigger superset, which was 21K classes, it had 14 million images. And we discussed this before, the dataset with 14 million to 300 million. That was the size at which Vision Transformer was having benefit. right? So one data set was the original ImageNet data set with just 1K classes. Second one is ImageNet with 21K classes with around 14 million images. Third is JFT, which we saw the custom data set built by Google with 18K classes and roughly 300 million high resolution images. We duplicate the pre-training datasets with respect to the test sets of the downstream tasks. So essentially what this means is, in these datasets, if there are images which may occur in some of the tasks which after pre-training, let's say you want to fine-tune the model to perform some other tasks. If there is any datasets that are present in that fine-tuning dataset as well as in the original pre-training dataset, you de-duplicate it, meaning you remove those datasets. You ensure that you are not, when you are looking at the benchmark performance, you are not having the same dataset which was part of the pre-training. We transfer the models trained on these dataset to several benchmark tasks. So here they are discussing about 5 benchmark tasks. One is ImageNet on the original validation label. So this is basically classification and cleaned up real labels. We will see what this is. Then CIFAR 10 or 100 dataset. So that's the third one. Oxford IIIT PET dataset. So this is also dataset with different PETs for segmentation, classification, or object detection. I can actually show you the Oxford dataset. So this is the data set in which there are a bunch of pet animal images with either bounding box or just class label or the semantic segmentation mask. Just the segmentation mask. So that's the Oxford IIIT pets data set. Oxford Flowers 102 data set is, or as the name suggests, basically a bunch of flowers. So this is how the dataset look like. Let's not go into the details of what exactly this dataset is. I mean, it's not too much relevant for our understanding. So these are the 5 datasets where we perform transfer learning. So the pre-trained model we use for tasks on these 5 datasets. For these datasets, they also followed certain pre-training, certain pre-processing. Okay, and before we move on, let's just look at this table because they are yet to talk about this table. But anyways, we can have a look at this. So they are talking about 3 vision transformer models which they constructed for this paper. So here, do you recognize what this layers is? It's the L. So L equal to 12, L equal to 24, 32. It's the number of transformer blocks occurring in series. This hidden size D is the dimensionality of the embedding vectors. So the base model had 768 dimensions, large had 1024, 1280. Then MLP size is how do you project? So if you have hidden dimension D, you in the multi-layer perceptron, you are projecting it into a higher dimensional space. And it seems like here you are projecting it such that it's 4x. So if this is 768, let's just check whether 768 multiplied by 4 is 3072. It is actually 768 multiplied by 4, 3072. So basically this is the projected dimension in multi-layer perceptron is 768 by 4. Same thing applies for this. 1024 multiplied by 4 is 4096. 1280 multiplied by 4 is, yeah, I think it's correct. Yeah, this is also 4x. So basically multi-layer perceptron size is 4 times D. D is the dimensionality. This is D. And then you project it back into whatever is the number of classes in your data set. So this dimensionality will be basically 21K if you have 21K classes, depending on what your data set looks like. Then the number of heads is the parallel attention heads in each multi-head attention in each transformer block. So there are 12 heads in each transformer block, and like that you have 12 transformer blocks in vision transformer base. For vision transformer large, number of heads was 16, number of layers was 24. So the total number of parameters in the model, base model has 86 million, then the next one has 307 million, and then the next one has 632 million. So you can see that this is unlike large language models, you would not call these as large language models. First of all, it's not a language model, but if you were to compare these models with typical large language models, you would call these as small models, right? We can even ask what is the number of parameters in a small language model? It could be between 1 to 10 billion or less than that. Okay, tiny / micro SLM 1 to 10 million, small SLM means small language model, medium SLM and large LLM. So medium SLM is what we just talked about, 100 to 1 billion. So GPT-2 medium, etc. And then if it is something above 1 billion, it's typically classified in LLM category. So right now we are definitely somewhere in this range, right? Small SLM or medium SLM, around that size. Okay. We also have one more task, the sixth task, apart from these five tasks. Sixth task is VTab classification suite. So VTab is basically this. We can ask again ChatGPT. Let me close some of these. Describe the VTab tasks dataset. Visual task adaptation benchmark. They consist of 3 different categories. So they also have a graph which shows these 3 categories, their results in these 3 categories. So I'll just jump ahead and show you the graph. Basically, they have natural tasks, specialized tasks, and structured tasks. And if you want to know the description of each of these, natural task is photographs from normal human life. So 5 flowers data, CIFAR 100, Caltech 100, 101, Oxford data. These are all normal data set that any humans may encounter in their day-to-day life. Specialized is domain specific, so satellite images, remote sensing, etc. Structured or synthetic, I guess, is computer generated scenes where structure matters. Clever, D-Sprite. So I'm not sure what these data sets are. Let's see. I have not used this. Okay, it looks like it's data set consisting of some kind of structure. So here there is shape, there is color, and also shininess, right? Three things I can see here. This is shiny, this is less shiny. Colors are the same. Shape, here this is both are the same shapes, but color is different. So I think this clever data set might be basically training data set of 70,000 images and these many questions, validation data set of 15,000 images and these many questions. Okay. I kind of understand what this data set is about. And let's go back. So that is structured or synthetic data. Either we can create it using computer generated like 3D rendering, or we can create it manually also. So there are different data sets like that. So I'll come to the results in a bit, but I just want to go through this section once. So VTab evaluates low data transfer to diverse tasks using 1000 training examples per task. The tasks are divided into natural, as we discussed, specialized, like satellite imaging, etc. Structures, tasks that require geometric understanding like localization, which we just saw. So then they are talking about their model variants. The base and large models are adopted directly from BERT, and we add the larger huge model. So base, large, and huge. Those are the 3 models. In what follows, we use brief notation to indicate model size and input patch size. So vision transformer L16 means it's a large vision transformer with patch size being 16. So it's very nice. Then note that transformer sequence length is inversely proportional to the square of patch size. Thus, models with smaller patch size are computationally more expensive. Makes sense, right? Because when you have less smaller patches, each image you are now dividing into more number of patches, because number of patches is n equal to HW divided by P square. So if the value of P, which is patch size, goes down, number of patches N goes up. So then computationally, the model has to take care of more number of tokens. For the baseline CNNs, we use ResNet, but replace batch normalization layers with group normalization. And use standardized convolutions. So let's see, we know what batch normalization is. Batch normalization is we normalize the mean and standard deviation of the dataset distribution within each batch. Let's see what is group normalization. What is group normalization. It's a type of normalization layer used in neural network, especially CNNs, aims to stabilize training by normalizing actions within group of channels instead of across a batch. We understand that it's different from batch normalization, but I just want to see what a group looks like. Independent of batch size. Okay, so how it works, suppose your input has this shape. So N is the batch size, C is the number of channels, H and W are the height and width of the image. Group normalization divides the channels into G groups, for example, 32 groups. Okay, so it's not looking along the batch dimension. So it's not looking along this dimension. It's looking along this C dimension. C is the channel. Then for each group, it computes the mean of the group and standard deviation or variance of the group, and you try to normalize with respect to mean. So from every single point, you subtract the mean and you divide by the standard deviation. Here, epsilon is added, I guess, so that division by 0 is eliminated. And then you add a learnable scaling and learnable shifting. So essentially, what happens is, let's say your values are like this. This can be for images or anything, okay? So let's say your x is equal to x1, x2, etc. up to xn. Let's say these are your pixel values in a certain group or in certain batch. This will have a mean, mu, and this will have a standard deviation, sigma. Then what is done is xi will become xi minus mu divided by sigma. So here what they are doing is you are doing sigma square plus epsilon, but let's say you're subtracting the mean and dividing by standard deviation for simplicity. Now, what is also done is, apart from this, so here there is no learnable parameter. Your mu and sigma is calculated from your xi's. Now, what is done is xi is actually converted into xi minus mu by sigma multiplied by beta I plus gamma I. So this beta I and gamma I are now trainable parameters. So if there are n parameters in your input, you will have 2n parameters, n number of betas and n number of gamma. So this is scaling, which is a learnable parameter, and this is bias or shift, which is again a learnable parameter. So this is typically how normalization is implemented. Here also same thing is being done. Your gamma and beta are the symbols that they are using. I use beta and gamma. Yeah, doesn't matter what Greek symbols you use, but I hope you get the idea. So the idea here is that instead of doing this along a batch of images, you do it along group of images along the channel dimension. So you divide the number of channels by certain number, and each of those channel group is one group, and within that group you calculate the mean and standard deviation and then perform the normalization. Okay, it's a minor digression, but I hope it's better to understand what's the difference between batch normalization and group normalization, and use standard convolutions. These modifications improve transfer, and we denote the modified model ResNet as ResNet bit. For the hybrids, where we do not feed the images directly, we feed the features. For hybrids, we feed the immediate or intermediate feature maps into Vision Transformer with patch size of 1 pixel. So this we had already seen earlier. The patch size in the feature map that we transfer to the Vision Transformer is 1 by 1. Each patch is 1 by 1 pixel. Later stages have lower. Yeah. So one thing which I wanted to note here is convolutional neural network, right? If you look at how the image transforms from layer 1 to, let's say, layer number 6. In layer number 1, you may have an image of size 224 by 224 by 3, something like this. In the next layer, this might become 64. In one of the next layers, this will become 64 by 64 by 12. And eventually what happens is, so here you see this is the spatial dimension and this is channel. So spatial dimension decreased, number of channels increased. And eventually this might become 1 by 1 by 1024 or something like this after multiple layers. So the spatial dimension has become very less. It's literally just 1 pixel, but your channel dimension will become more. So spatially, if you look at the image, you won't be able to say whether it's a cat or school bus or whatever, but spatially it will be capturing abstract features. And because there are large number of channels, you can capture more and more number of abstract features to represent your image in smaller number of parameters. So here to represent the image, you have 224 by 224 by 3, that many numbers, that many pixel values. Here on the other hand, in just 1024 numbers, you are trying to represent all the information that is contained in this input image. So this is what I have written here, saying later stages have lower spatial dimension. So I guess that's also one reason why the feature map is not again chopped into, smaller patches. The patches themselves are 1 by 1 pixels. To experiment with different sequence lengths, we either take the output of stage 4 of a regular ResNet. So stage 4 of a regular ResNet will be something. We can see that if we just look at ResNet 50, that is one option. So you take the feature map from the stage 4 of ResNet. So this is for hybrid, okay, not for pure CNN or not for pure vision transformer. This is for hybrid, where you extract the feature map. So in one option, you directly take the feature map from stage 4, or you remove stage 4, place the same number of layers in stage 3. So basically stage 3 you replicate as stage 4, and then take the output of this extended stage 3. I'm not sure what exactly is the reason why they did this rather than maybe taking output from stage 3 itself. Maybe because in stage 3 the spatial dimension might be higher. So if you go one more stage, you will get reduced spatial dimension. So perhaps that's the reason. And then option 2 results in a 4x longer sequence length and a more expensive vision transformer model, because in option 2 we are using stage 3 one more time. So I guess we are not reducing the spatial dimension when you go from stage 3 to once again going to stage 3. So because a spatial dimension is not reducing, you will have more number of patches, and because of that, I guess your vision transformer will become more expensive to train. This is what I understand from this paragraph. Maybe there are loopholes in my understanding, but from what is written, this is what I'm imagining. All right. Now let's go to details about training and fine-tuning. In pre-training, this paper uses ADAM. So ADAM is the optimizer, adaptive moment. And the first and second moment values are 0.9 and 0.999 with a batch size of 4096. And high weight decay of 0.1. So weight decay is basically, there will be a lambda W term. So lambda W is like you are multiplying the weight by a lambda term to penalize your weight from becoming larger step after step. So basically you want to shrink the weights a little bit after every step. So this is what is called as weight decay. And here the number 0.1 is a bit high, which I don't know why it was helpful in this particular case unless I run the experiment myself. It's hard to say, but I guess they figured it out after a bunch of experiments. Then we use linear learning rate warm-up and decay. So learning rate eta is not immediately set to a high value. It slowly increases, and so it warms up and then decays later in the later parts of training epochs. For fine-tuning, we use stochastic gradient descent with momentum. So for training, they use ADAM, and fine-tuning, they use stochastic gradient descent. Batch size of 512 for all models. For ImageNet results, see table 2, which we will come to. Fine-tune the model at high resolution. 512 was the image resolution for vision transformer large, 16 pixel as the patch size. And 518 was the resolution for vision transformer huge, with 14 as the patch size. So 14 patch size means this vision transformer for the same image size will have more number of pixels. And also used a Polyak and Juditsky averaging factor of 0.9999. So I was not very familiar with this factor before reading this paper. So while reading the paper last time, I understood what this averaging is. Basically, instead of using the model weights from the latest training step, so the new weights equal to old weights minus eta times dou by dou weights of the loss. That's how usually you do the gradient descent. So weights I equal to weight I minus 1 minus eta times dou loss by dou weights I or I minus 1, right? Something like this. Instead of this, you consider a moving average of weights over several training steps. So this is called weight averaging or exponential moving average. So this averaging with a factor of 0.9999 utilizes not the weight from the immediate run, but a moving average of weights from the past several runs. Then metrics. We report results on downstream data set. either through few shot or fine tuning accuracy. We'll come to what exactly few shot or one shot or fine tuning is in the upcoming sections. So because when we see the results, it will be more clear. Fine tuning accuracies capture the performance of each model after fine tuning on the respective dataset. What is the respective dataset? They are using CIFAR 10 or CIFAR 100, and they have VTAB tasks. So there were 6 different tasks on which fine tuning is done. Few shot accuracies are obtained by solving a regularized least squares regression problem that maps the frozen representation of a subset of training images to target vectors. So it looks like a bit of a complex sentence, right? Let's do one thing. Let's take a screenshot and ask ChatGPT to kind of rephrase this sentence. Explain the fine tuning part. So it is fine tuning with, actually it's not fine tuning, it's a few shot. Explain the few shot accuracies part. So I understand that you take the frozen model and take a sample data point, convert the sample data point into some sort of representation. But what I don't understand is what are we regressing on here? Because I thought the weights were fixed. So this is a natural question that we can have. So regression, that okay, instead of fully free training on the model again, you freeze the pre-trained representation, the output features of the network, I understand that, and train a simple linear model, specifically a regularized least square regression on top. Okay, makes sense, right? So you have the fully trained model. This is the fully trained vision transformer model. On top of this, you add one more layer, maybe like a linear projection, basically one extra hidden layers, and the weights in that alone you will train. So weights in this you will train. So the inputs that are coming into these weights are the final output representation of whatever is your input image. So input image is X. X goes into vision transformer. Vision transformer produces the output representation. This is frozen. So vision transformer weights are not changing, but this can be changed. And then whatever comes out of this, W will convert into the final output Y. So if I call this as Xi, and if I call whatever is coming here as X for convenience, so that the formula here is matching, then we say Wx is the prediction. This is equal to Y cap, and Y is the reality. So now we need to find what's the difference between Wx and Y. So the difference between, or XW, to make sure that the dimensionality is matching with Y. So XW minus Y, and you have to minimize this such that you have to minimize the value of this. And for that, you have to find the optimum value of weights in this extra additional layer. But not just that, you are also having a regularization parameter here, which is lambda times modulus of W square. So this ensures that the weights in this additional part, which is part of a few shot accuracy calculation, it's not too big. It's not overfitting. So that is what is done here. So this formulation allows us to recover the exact solution in a closed form. Though we mainly focus on fine-tuning performance, sometimes we use linear few shot accuracies for fast or on-the-fly evaluation, where fine-tuning would be too costly. Why would fine-tuning be very costly? Fine-tuning will be very costly because in fine-tuning, this entire architecture weights you are changing. It's not frozen. But in few shot accuracy calculation, you are simply training an extra additional layer whose weights will alone change. The rest of the entire big vision transformer architecture remains unchanged. Okay. So that is what this paragraph about metrics is saying. Now, comparison to state of the art. We first compare our largest models, Vision Transformer Huge with 14 as the patch size and Vision Transformer Large with 16 as the patch size, to the state-of-the-art CNNs from the literature. The first comparison point is Big Transfer BIT, which performs supervised transfer learning with large ResNets. So we can also ask, what is Big Transfer model? What is Big Transfer BIT model? So this must be a ResNet based model, a CNN model for performing image classification. BIT is a transfer learning recipe for computer vision proposed by Google Research, pre-training a large CNN on a very large supervised image dataset for sure, then fine-tune or adapt the model to many diverse downstream tasks. Use a simple recipe that emphasizes scale, which is data plus model size, and robust transfer. So large upstream dataset plus big architecture. So BIT-S was trained on the ImageNet data with 1.3 million. So this is the 1K class classification dataset. Bit medium and bit large on 300 million. So here what they are saying is bit transfer idea, it's not necessarily a model name. The model could be any big model. So you use a large ResNet as the model, then you perform supervised transfer learning. So you teach or you pre-train the ResNet, and then you perform transfer learning for further fine-tuning task. The second is noisy student, which is a large efficient net trained using semi-supervised learning on the ImageNet. So here, I'm not sure what exactly do they mean by semi-supervised learning, although I know several ways in which semi-supervised learning is implemented. So I just want to know exactly what it means, sir. So here, explain semi-supervised learning in this context from the Vision Transformer paper. Also, explain what is noisy student. So I just want to understand these two terminologies. Semi-supervised learning in the context is you have model learning on your initial label datasets. Then it uses trained model to predict pseudo labels for a huge pool of unlabeled images. Okay. Then pseudo labeled samples are treated as additional training data. The model is then trained on the combination of real plus pseudo labels. Okay, so real labels are your actual label data, ImageNet 1K or ImageNet 21K, whichever it is. Then for a new data set, you predict pseudo labels. So now pseudo labels are the model will predict on a new unseen data set what the labels would be. And then the real label data and the pseudo label data, you use both of them to retrain or sort of fine tune the model. So this setup is called semi-supervised because it mixes supervised learning and unsupervised data. All right. What is noisy student? Noisy student is a semi-supervised learning method that builds on teacher-student framework. Teacher model is like a large model trained on labeled data. Pseudo learning is the teacher will generate labels for millions of unlabeled images. Then student training is train a larger efficient net, which is the student, on both the labeled and pseudo labeled data. Okay, I think we understand what this means. Okay, so that also they use. Currently, noisy student is the state of the art on ImageNet and bit large on the other dataset reported here. All models were trained on TPU v3 hardware, and we report the number of TPU v3 core days taken to pre-train each of them. That is the number of TPU v3 cores. 2 cores are there per chip used for training, multiplied by the number of training time, multiplied by the training time in days. So basically, how many cores did you use? If you use 5 TPU v3 cores, and let's say the training time is 2 days, you multiplied 5 by 2 to get total 10 training days, something like that. So that is the total TPU core v3 days. So TPU is different from GPU. TPU was specifically designed by by Google for processing tensor. So GPU is graphical processing unit. TPU is tensor processing unit. Then table 2 shows the results. The smaller Vision Transformer large 16 model. So smaller means compared to the huge Vision Transformer huge 14 patch size is of course bigger than Vision Transformer large 16 patch size. Model pre-trained on JFT 300 million outperforms BIT-L on all tasks. So BIT-L was using ResNet, which is a convolutional neural network, on a big data set and then performing transfer learning. And here they're saying, here what they're saying is even this relatively smaller model performs better than the BIT-L framework on all tasks while requiring substantially less computational resources. The larger model, Vision Transformer Huge, with 14 as the patch size, further improves performance, especially on more challenging tasks like ImageNet CIFAR 100 and VTAP Suite. So here by ImageNet, probably I mean it's ImageNet 21K. I'm not 100% sure. I guess this is ImageNet 1K because they mentioned in the paper before that For whenever we talk about ImageNet 1K, they will just refer to it as ImageNet. Okay. Interestingly, this model still took substantially less compute. Which model? Vision Transformer Huge with 14 as the patch size. It still took substantially less compute to pre-train than prior state of the art. However, we note that pre-training efficiency may be affected not only by architecture choice, but also other parameters such as training schedule, optimizer, weight decay, etc. For sure. We provide a controlled study of performance versus compute for different architectures in section 4.4. We will see that once we reach the figure. Finally, Vision Transformer large 16 patch model pre-trained on public ImageNet 21K. So this is a big data now with 14 million images. It performs well on most datasets too, while taking fewer resources to pre-train. It could be trained using a standard cloud TPU v3 with 8 cores in approximately 30 days. So of course, training is taking time, but compared to state of the art, it's much faster. So let's check if we missed any table in the previous. No, we went through this table. And here, what they are showing is the efficient or the accuracy of the model. So ImageNet is the small ImageNet data. This is also ImageNet with better labels, I guess. CIFAR 10 dataset, CIFAR 100, Oxford IIIT patch dataset, Oxford Flowers, and VTab 19 tasks dataset. And these tasks were in 3 different categories. Basically, images were, they are natural, specialized or structured. Then hours JFT means you are using the Vision Transformer Huge with patch size 14 model, which is trained on JFT dataset, which is 300 million. You are fine-tuning it on each of these and see what is the accuracy. Hours JFT Vision Transformer Large 16 is the Vision Transformer Large model. Hours 121K Vision Transformer Large 16 is again, I don't think this is 121, this is I21. I'm not sure what this is. What is this I21K? I'm not sure what this data set is. I don't remember we reading about this in the paper before, or maybe I just missed it altogether. I just want to know hours referred to the ImageNet. Okay, I21 is simply ImageNet 21. Okay, all right. Then bit L is not hours. Now this is the state of the art. Okay, SOTA. This is state of the art. This is also state of the art. These two, but these 3 are from the paper. So you can see how for each of these fine tuning. So this is 1, 2, 3, 4, 5, 6, 7. So there are 7 fine tuning mentioned here. Here, Vision Transformer Huge works the best, 88.55. Vision Transformer Huge, Vision Transformer Huge. So in almost all the tasks, all the data sets for fine tuning, Vision Transformer Huge works the best. For the Oxford Flowers alone, Vision Transformer Large works better. In any case, it is beating the state of the art for all these data sets, right? So let's read the table description. Comparison with state of the art on popular image classification benchmarks. What are those benchmarks? These seven items. These 7 items are the different benchmarks. We report mean and standard deviation of accuracies averaged over 3 fine-tuning runs. So the mean, this 77.63 plus or minus 0.23, it is a mean over 3 runs and standard deviation over 3 runs, 3 fine-tuning runs. Vision Transformer models pre-trained on JFT 300 dataset outperform ResNet baselines for all the tasks. Isn't that correct? Because this is also JFT pre-trained, this is also JFT pre-trained, and combined, if you consider this huge model and large model, they combined outperform in every single task, they outperform the state of the art on all the tasks, all the datasets, while taking substantially less computational resources. So here, computational resources is mentioned in the last column, last row. So 2.5K TPU, I think this is TPU, yeah, TPU v3 core days, 2.5K days. This one is 0.68K days. This is 0.23. But then these two are 9.9 and 12.3. So of course, Vision Transformer Huge takes more time to pre-train. This is the time it takes for pre-training, not for fine-tuning. Fine-tuning is much faster. So this is much faster than either this or this in terms of the number of TPU v3 core days. Vision Transformer pre-trained on smaller public ImageNet 21K dataset performs well too. Slightly improved 88.5% result reported in Turon et al. So what do I mean by that? So this is the ImageNet 21K dataset pre-trained model. This guy, which I got confused what this I21K was. So here, this one is not better than this. This is also not, this is not, but 93.25, 94, 99.61, 72 point. I don't know which one slightly improved 88.5% results reported in Turon et al. 2020. But I don't see where exactly it is performing. Okay, it does not say performs better. It just says perform well. Yes, for sure. It's performing almost similar to the state of the art, although the numbers on an absolute scale are slightly lower. But look at the computational resources. It's taking less than 1/40th of the resources. So it's very, very efficient that way. Now, the VTab we said there are 3 different tasks: natural, specialized, and structured. So how do you read this figure 2? So first, just look at these 3: natural, specialized, and structured. So there are 7 plus 4 plus 8 images from these many different types of tasks are there. It doesn't mean there are 7 images. There are a lot of images, but they belong to these type of tasks. Natural could be like people, animals, or things like that. Specialized, as we said, it's like images from satellite, etc. Structured is those colored geometric shapes with different matte finish or kind of shining finish, etc., etc. Then 7 plus 4 plus 8, 11 plus 8, 19. So this is just an aggregated graph. So here you can see that this blue graph is Vision Transformer. It is outperforming bit L or Vivi X100 or S4L. I don't know what are these. I guess this is ResNet 50 models. So this is ResNet 152 model. This is ResNet 50. This is ResNet 50. This is Vision Transformer Huge. We don't have to necessarily go into the details of what are these models. I guess they are the state of the arts for the VTab dataset. That's what I understand from what they have plotted. And you can see that the blue curve, which is Vision Transformer's performance accuracy, is better compared to any other state of the art models. Okay. So this we already discussed. Figure 2 decomposes VTab tasks into their respective groups. Yeah, we saw that. There are 3 groups and compares to previous state of the art on this benchmark. Bit, Vivi, it's a ResNet co-trained ImageNet and YouTube. Yeah, this we already discussed. And S4L, supervised plus semi-supervised learning on ImageNet. So this we know what is supervised plus semi-supervised. We produce labels on a unlabeled dataset using an already pre-trained model. That pre-training would have been done on a supervised data. Then this produced labels plus the already existing labels are used for training a slightly bigger model to produce a new model. And that new model is essentially undergoing supervised plus semi-supervised learning. Vision Transformer H14 outperforms this and other methods on natural and structured tasks. On the specialized, the performance of the top 2 models is similar. Yeah, for sure. On the specialized, this blue and this, what was this? The bit large. These two have similar performance, but still slightly Vision Transformer Huge is performing better. So in general, we can say Vision Transformer Huge is always performing better. And this is just a description of VTab that I had written earlier, Visual Task Adaptation Benchmark. So VTab provides a comprehensive test of how well a pre-trained model can transfer to many different types of visual problems. So types of visual problems means visual problems that involves images from natural settings, visual problems that involve images from like specialized settings, like let's say maybe medical images or satellite images, and ones that involve synthetic data or structured data like that geometric shapes. Okay. Now, pre-training data requirements. So Vision Transformer performs well when pre-trained on large JFT 300 million dataset that we saw already here. So this was JFT 300 million, this was JFT 300, this was huge model, this was large model, and they were performing very well. With fewer inductive biases for vision than ResNets, how crucial is the dataset size? We performed 2 series of experiments. So here what we are trying to understand is convolution operation has the inductive biases like translation, equivariance, or locality. So those features are there. Transformers do not have those features. They just have global attention. So here, in the absence of those inductive biases, which are available in the state-of-the-art ResNet models, how crucial is the size of the dataset? What if we reduce the dataset size? So for confirming this, they do a few more experiments. First, we pre-train vision transformer models on datasets of increasing size. So ImageNet is ImageNet with 1K. ImageNet 21K is 21K classes. GFT 300 is 300 million classes. Actually, not 300 million classes. It's 300 million images. Number of classes, if I remember, was 18K or something. This one had 14 million images. This is 300 million images. To boost the performance on smaller datasets, we optimize 3 basic regularization parameters: weight decay, dropout, and label smoothing. So label smoothing is nothing but, instead of saying that the ground truth is 100, instead of saying such a hard label, you say it could be 1 minus 2 epsilon, and this epsilon will say, epsilon, it's let's say 0.1. Then your ground truth will be 0.8, 0.1, 0.1 instead of 100. So instead of making a hard prediction saying 100% it's a dog or a cat or something like that, you will not penalize the model even if the model says it's 80% a dog, something like that, right? So this is this is label smoothing. Figure 3 shows the result after fine-tuning to ImageNet, and results on other datasets are shown in table 5. We can see the table and figure. When pre-trained on smallest dataset, which is ImageNet 1K, vision transformer large models underperform compared to vision transformer base models. Very important. Which one is bigger model? Vision transformer large model is bigger. Vision transformer base model is the smallest among the 3: base, large, and huge. Despite regularization. So despite introducing regularization on small dataset, vision transformer large model underperforms. With ImageNet 21K pre-training, their performances are similar. So this is the larger dataset. So on larger dataset, base and large model for vision transformer, they both perform similarly. Only with JFT 300 million data, we see the full benefit of larger models. Why? Because JFT 300 million has around 300 million images. ImageNet 21K has only around 14 million images, correct? Now we just want to see the figure. Figure 3 also shows the performance region spanned by bit models of different sizes. The bit CNNs outperform vision transformer on ImageNet. So this we expect bit CNN outperform vision transformer on ImageNet. ImageNet is just the ImageNet 1K. ImageNet 1K is a small dataset. On small dataset, bit CNN, which is you train ResNet, and then the ResNet is used for transfer learning, which is basically convolution based transfer learning. That one outperforms vision transformer, but with larger dataset, vision transformer overtakes. So let's see what the figures are saying. We have few figures to go through, figure 3, 4, and 5. Let's see what these figures are showing. So figure 3 is transfer to ImageNet. While large vision transformer models perform worse than bit when pre-trained on small datasets, they shine when pre-trained on larger datasets. Similarly, larger vision transformer variants overtake small ones as dataset grows. Let's see how this figure is depicting that. So on x-axis, you have the dataset, pre-trained dataset. This is ImageNet 1K, ImageNet 21K, JFT 300 million. So JFT 300 million is the biggest dataset. Now let's see where the vision transformer is lying. So first of all, this gray is, there are basically like a gray region. It's a series of bit models, okay? Bit models mean it's a series of ResNets pre-trained on these 3 datasets, either of these 3 datasets, and it shows the range of performance. So for ImageNet data, the bit models have a range of performance in this range. For ImageNet 21K, the bit models have a performance in this range. Similarly, for JFT 300, the bit model has a performance of this range. Now let's see how vision transformers compare against this. Which vision transformers? The base model with 32 as the patch size, base model with 16 patch size, large with 32, large with 16, and huge with just 14. Now first let's see how does vision transformer compare against bit for the smallest dataset. For smallest dataset, the best performing vision transformer model is vision transformer base model with 16 as the patch size, this pink guy. Second best performing one is vision transformer large. Then vision transformer large 32 is the worst. Vision transformer large 16 is second best. Vision transformer base with 32 as the patch size is is also not good. So in general, you can see vision transformers, which are these four on this, is worse compared to the range of bit. Range of bit is over here. And why is this the case? Because this is a small data set. This is 1K images. Sorry, 1K classes. Only around 1 million images or something, 1.4 million. But as the image data set size increases, so here you have 14 million. So for this, you have 14 million. For this, you have 300 million. For 14 million, you can see generally vision transformers are going up. The large model is now performing as good as the state of the art. The base model with 16 as the patch size is almost there. The other two models are slightly below. And now let's look at the largest data size, JFT 300 million. So now the vision transformer huge model is outperforming the state of the art, which is the bit. State of the art up until this point, until the point when this paper was published. So this is where you can see that in general vision transformer performance. So y-axis is accuracy. So accuracy is generally shifting from the range of 70 to, let's say, 77. From there it's shifting to 80 to 87. And from there it shifted to 82 to 89, 90, somewhere around that range. So in general, accuracy is shifting to upper direction as the model, as the data set size increases. Now, how about this? Number of JFT pre-training samples versus linear 5-shot ImageNet top 1%. I don't think we read the section corresponding to this figure yet. I'm not sure we read this, but in any case, we can read the figure. Linear few shot evaluation on ImageNet versus pre-training size. So here, we are performing few shot evaluation on ImageNet. It's not fine tuning. It's just few shot evaluation. We know what is few shot evaluation. In few shot evaluation, we have vision transformer with frozen weights. This we discussed before. We have frozen weights. And then we have one additional layer whose weights are now changed during training using regularized regression. And then prediction is made, right? So here, let's look at the data set size. So JFT with 10 million all the way JFT till 300 million samples. And here, what you can see is the ResNet models, ResNet 50, which is bit, ResNet 52 or 152, which is also bit. So bit is just the name for the technique as we saw here. Bit is simply what is big transfer model, bit. Bit is a transfer learning recipe. So it's not a model. It's a transfer learning recipe, which was proposed by Google. So you train on a large data set, you train a big model, and then you do transfer learning after that. So bit is just the name for that. But the model that they're using here is ResNet 152 and ResNet 50. Now, let's see which model performs the best in 300 million. In 300 million, vision transformer large 16 performs the best. Okay, that is first observation. Second observation is vision transformer base model is performing the worst among all. ResNet 50, which is also one of the state of the art, it's not performing that great. Its learning capability has already saturated. It's not improving at all by increasing this by 30-fold, the dataset size by 30-fold. Similarly, ResNet 152 is also not improving significantly in these three dataset sizes, 30 million, 100 million, and 300 million. There is not much difference in the accuracy of few shot transfer. On the other hand, you look at the vision transformer models, like for example, this green one is vision transformer large 32. The accuracy is yet to saturate. It is not saturated yet. It can go maybe one or two more dataset size order of magnitude increase. Similarly, this blue is vision transformer large with 16 as the patch size. It is also yet to saturate. Although it seems like in the last two dataset sizes, the accuracy is only marginally increasing. We don't know what the effect would be if we had like 800 million as the dataset size. So here what this figure description says is ResNet perform better with smaller pre-training datasets. You can see that these gray lines are above the blue or green or yellow lines. They are the two ResNet models. But they plateau sooner than vision transformer, which performs better with larger pre-training. So with larger pre-training, this blue is above. There is, however, this ResNet, this black line, which is ResNet 152, is still up there. But you can see that the vision transformer has overtaken ResNet for the two larger datasets with 100 million and 300 million. All right. Now this graph, let's also look at this graph. So these two graphs are the transfer learning accuracy on the y-axis, and on the x-axis is the total pre-training compute required in exaflops. So flop is one floating point operation, like one arithmetic operation, like adding two floating point numbers or subtracting, etc. Exaflop is 10 raised to 18 number of flops, so 10 raised to 18 calculations. So how much pre-training compute is required to achieve a certain level of accuracy for different models. So let's just look at this ImageNet data. So this is the 1K ImageNet data set. So if you increase the compute, so as the compute increases, meaning as the pre-training happens for more and more, the accuracy of almost all the models are increasing. It goes from 75 all the way till 90. And you can clearly see that for more compute, the transformer is vision transformer is better than bit or hybrid. Basically, the gap between vision transformer, bit and hybrid are reducing as the compute increases. For lower amount of compute, here you can see that clearly vision transformer is better. So to get 82% accuracy, you have to do a compute of 100 exaflops for ResNet bit. But for vision transformer, you just need to do let's say 20 exaflops or less than 20 exaflops. So that is how you can read the graph. We can also read the description: performance versus pre-training compute for different architectures. Let me just bring the highlight. Vision transformers, ResNets and hybrids. Vision transformers generally outperform ResNets with the same computational budget. As you can see, for the same computational budget, so let's say your computational budget is over here, 20 exaflops, vision transformer is above ResNet. Then hybrids improve upon pure transformers for small model sizes. Where do we see that? Over here. So here, this is hybrid, this is hybrid, this is hybrid. In general, hybrids are above the vision transformer for relatively smaller model sizes. So relatively smaller model sizes require relatively smaller computation. However, for larger sizes or with more computes, the difference between hybrid and vision transformer vanishes. So here, hybrid and vision transformer have pretty much similar performance. Same here. So that is what this graph is trying to say. Now let's go ahead. So now we are reading the text, which is yet to describe this figure number 5. Second, we train our models on random subset of 9 million, 30 million and 100 and around 100 million. We read it as 100 million, but it's 90 million to be exact. Which one is the graph? Figure number 4, this one. As well as the full JFT 300 million dataset. We do not perform additional regularization on smaller subsets and use the same hyperparameters for all settings. This way, we assess the intrinsic model properties and not the effect of regularization. So here what they're saying is, when we are performing few shot or 5 shot prediction, so this figure 4 is actually linear few shot evaluation, we don't add additional regularization parameters over here. So earlier we saw that there was one regularization. It was argmin of xw minus y. This was what we were trying to minimize, plus lambda times modulus of w square. So this was the regularization parameter. But here what they are saying is, we do not perform additional regularization on smaller subsets. So here I'm not exactly sure by additional regularization, do they mean they don't perform any regularization outside of this? That I'm not sure. Or whether they don't perform even this regularization, that I was not sure here, on smaller subsets, and use the same hyperparameters for all settings. This way we assess the intrinsic properties of models and not the effect of regularization. Because see, when you do regularization, you of course can have bigger models perform better, and it can reduce the overfitting and it can make the testing performance improved. But here they don't perform excessive regularization to see intrinsically whether the small models are better or not. We do, however, use early stopping. Early stopping is also one of the regularization techniques, but it's not a parameter based regularization, and report the best validation accuracy achieved during training. To save compute, we report a few shot linear accuracy. We report few shot linear accuracy instead of full fine tuning, because full fine tuning means you are not freezing the model, vision transformer model. You are training it entirely. Training as in not pre-training. You are changing all the parameters. But here, they are just comparing the accuracy for few shot linear model. Figure 4 contains the results. We saw that vision transformers overfit more than ResNets with comparable computational cost on smaller data sets. So here you can see that vision transformer is overfitting compared to ResNet, and that is the reason why the validation accuracy is so low. No, this gray one is not there, but these are the vision transformer that are overfitting compared to ResNet for smaller data sets. However, so for example, vision transformer base 32 is slightly faster than ResNet 50, but it performs much worse for 9 million dataset, but much better on 90 million dataset. Same is true for ResNet 152 and vision transformer large. So basically, ResNet 152 performs worse compared to vision transformer large for 90 million, or rather 300 million datasets. So 300 million, this is the, and even for 90 million, ResNet is below the vision transformer large. Okay. And this result reinforces the intuition that convolutional inductive biases is useful for smaller datasets, but for larger ones, learning the relevant patterns directly from data is sufficient, even beneficial. So I have just added a star here because this sentence summarizes a lot of things what this paper is trying to say. What this paper is trying to say is convolution as an operation can extract a lot of two-dimensional information because the filter itself, CNN filter itself, is two-dimensional. On the other hand, in transformer architecture in vision transformer, you don't know the spatial information. Apart from a learnable position embedding vector, you don't have any inherent two-dimensional position information present in the data. Whatever is there has to be learned. So for smaller data set, the convolutional inductive biases, what are the inductive biases we discussed? Locality and translation equivariance. It is very beneficial for smaller data sets, and because of that, ResNet outperforms vision transformer for small data sets. However, for large data sets, vision transformer can learn patterns in the data directly, even in the absence of convolutional inductive biases. Overall, the few shot results on ImageNet on figure 4, as well as low data results on VTab on table 2, seems promising for very low data transfer. So low data result on VTab is where? On table 2. Table 2 is this. Low data result on VTab is, I guess, this one is low data, I guess, because this is ImageNet 121, but this is JFT 300 million, this is JFT 300 million. So this one is almost comparable to this, but look at the compute, 0.23 versus 9.9. So I think here when they say VTab, VTab table 2 low data results, I hope they are talking about the third column from the right. Seem promising for very low data transfer. So when they say very low data transfer, they mean transfer learning. Further analysis of few shot properties of vision transformer is an exciting direction of future work. All right. Now let's see a couple more things. Scaling study. We perform controlled scaling study of different models by evaluating transfer performance from JFT 300 million. So data set they are keeping at JFT 300 million, and they are seeing how well maybe models of different sizes can perform. In this setting, data size does not bottleneck the model performance, and we assess the performance versus pre-training cost of each model. The model include 7 ResNets, which are ResNet 51, ResNet 52, ResNet 101, 1, ResNet 152, 1, 152, 2. Let's see what's the difference between, let's say, ResNet 52 and ResNet 152, 1. So let's ask GPT, what does ResNet 152 by 1 and 152 by 2 mean? Okay, so the multiplier is basically width multiplier. Width is number of channels in each convolutional block. So number of channels is the Z stack of each image. So if an image is 224 by 224 by 3, where 3 is the RGB channels. After some layers, it may become 64 by 64 by 16. And let's say this is what is happening in ResNet 52 or ResNet 50 by 1. In ResNet 50 by 2, this will become 64 by 64 by 32. The number of channels will double. So that is the ResNet. So it's basically the width of the model. Depth means you are adding more number of layers. Width means in each layer, your number of channels are more. Then pre-trained for 7 epochs plus R152.2 and R203 pre-trained for 14 epochs. Then 6 vision transformers were tried. Base model with 32 as batch size, base model with 16, large with 32, large with 16, pre-trained for 7 epochs plus large with 16 and huge for 14 are pre-trained for 14 epochs. Basically, they are picking different epochs for training larger models. And then 5 hybrids. So ResNet 50 plus vision. So ResNet 50 plus vision transformer base 32 means you will extract the features from the 4th layer of the ResNet 50 as we discussed earlier. And those features are now converted into patches of size 1 by 1 and they are fed into the vision transformer. Similarly, ResNet 50 plus base 16, large 32, large 16, etc. for 7 epochs plus ResNet 50 plus large 16 for 14 epochs. Basically, they're now having bunch of different models of different sizes, all trained on the same data set to see how the size of the model affects the accuracy. As simple as that. Figure 5 contains the transfer performance versus total pre-training compute. Figure 5 we already saw actually. Figure 5 was the total training compute versus transfer learning accuracy. And this actually, you know what, this compute time is dependent on the model size. So bigger models will have more computes, okay? So in general, you can assume that the models on the right are bigger models because they have more compute requirement. Models on the left are smaller models, left of the x-axis in both of these graphs. Okay. First, vision transformer dominate ResNet on the performance/compute trade-off. So how do you know that vision transformer dominate ResNet on performance divided by compute trade-off? Look at this. Consider the same performance for 2 models. So let's say performance is around 80%. Which one requires more compute? More compute is needed for ResNet compared to vision transformer. So performance divided by compute means if the denominator is smaller, that one will have a better value. Which one has denominator smaller? Whichever has better, lesser compute requirement. So this vision transformer has lesser compute requirement compared to this ResNet. So in general, for the same compute, you will find vision transformer on the left-hand side of the x-axis in general compared to ResNet. And then that's the first thing. Then vision transformer uses approximately 2 to 4x less compute to attain same performance averaged over 5 datasets. So averaged over 5 datasets is the left-hand side graph. So to achieve the same performance, so let's take the same performance. This is the same performance. This is vision transformer. This is ResNet. How much is this? This is 10 raised to, this is around what? 110 or 105 exaflops. This is maybe 15 exaflops, right? So 15 versus 105, it's almost like an order of magnitude difference. In many other cases, so this is 115 and this is 200, 300, 400. This is around 450 or something. So there is a 4x difference here between these two. I mean, this graph is logarithmic. So this is 450 because this is 100. This is 200. Actually, this is not 115, by the way. This is 200 and something. So 200, 300, 400, 500, 600, 7, 8, 9, then 1000. So this is not 115. This might be maybe 215 or something like that. So there is a 2x, something like 2x factor here. So, and here this will be, this is 1, this is 10, 20, 30, 40, 50. Actually, some lines are missing, I guess, but I hope you get the idea of the logarithmic graph. So that is what they are saying. In general, vision transformer uses 2 to 4x less compute to train to achieve the same performance. Second, so that's the first takeaway. Vision transformers are more efficient in terms of compute for attaining the same accuracy. And when we say compute here, we are talking about pre-training on JFT 300 million data. Second, Hybrids slightly outperform vision transformer at small computational budgets. We saw that hybrids were slightly above, but the difference vanishes for larger models. So we have seen that the hybrid, which was these orange color plus dots, they are closer and closer to transformer for larger computes, meaning larger models, but they are better performing than vision transformer for smaller compute or smaller models. That also we saw. And that's the second takeaway. Third is, this result is somewhat surprising since one might expect CNN local feature processing to assist vision transformer at any size. So what does this mean? This means if we are extracting features from the CNN and then feeding into transformer, it must be better than directly feeding the image to vision transformer, right? Because CNN is already good at extracting features, and those features, on top of those features, is when what the transformer is trying to learn. If the transformer tries to do that, that should be better, meaning hybrid should always be better according to the idea of what the convolution operation can do. However, clearly we can see that vision transformer is outperforming everything for larger data sets or for models which require larger compute. Here it's not larger data set is the same. Here it's about larger model which requires more compute. Those models of pure vision transformers are outperforming hybrids, or it's as good as hybrid. Third, vision transformer appear not to saturate within the range tried, motivating future scaling effort. How do we know that? You see, vision transformers are still improving its performance as the compute is increasing. Maybe what this means is you can still go to higher sizes of vision transformer models and it will improve the performance even further, above 90% perhaps. Okay, then inspecting vision transformer. So now we will see what vision transformer is trying to see during its inference. To begin understand how the vision transformer processes image data, we analyze its internal representations. Internal representation would be what? It could be just visualization of the attention values, attention weights, or just the attention weights for a particular input image. The first layer of vision transformer linearly projects the flattened patches onto a lower dimensional space. We know this, right? First layer of vision transformer basically converts image patches into D-dimensional representation. And D was 768 for the small model, 1024 or something for the big model, for the large model, and for the huge model, I think it was 1280 or something like that. So that was the dimensionality, but still the dimensionality was in a lower dimensional space compared to the number of values in the patch. Figure 7 left shows the top principal components of the learned embedding filters. So this time, let's go to the next page to see what is figure 7. So learned embedding filters. This is a very important figure. So these are the first 28 principal components of the filters that convert what to what? Filters that convert X into Z0. Or Z before before the first layer of the transformer, meaning the input X. You remember this, right? X multiplied by E plus position. Let's say E pos was Z0. You know this from the equation which was discussed in the second or third page. Yeah, this one. So Z0 is equal to X times E. You also prepend a classification token plus position embedding. Okay, so this 0 will go to the first transformer block. Then from that Z1 will emerge. Then Z1 will go to second transformer block, and so on. Like that, there are, I think, 12 transformer blocks in the base model. Yeah, there are 12 layers in the base model, like that. Now let's go back. So figure 7 shows the top principal components of the learned embedding filter. So now what is the learned embedding filter? By the way, who is performing the embedding here? This guy, this E is performing embedding. E is converting X into Z before position embedding. Position embedding is anyway added. So these are now the principal RGB embedding filters. It's first 28 principal components. So I guess it's the 28 channels or 28 layers in the filter. All right, I'm actually not sure if it is 28 layers or not. Let's ask ChatGPT since I don't want to assume. So in vision transformer does 28 principal components in the filter mean 28 channels? Let's see. Okay, they are not 28 channels. So what I just said was wrong. It's not 28 channels. They are 28 principal directions or basis vectors capturing dominant variation. So I think this is more like some sort of principal component decomposition. You are decomposing it into top 28 principal components. So what is happening in vision transformer? You have 16 by 16 by 3 patch, which has 768 values. But these 768 now you have to convert into d-dimensional embedding. So each embedding dimension has a size of patch square multiplied by 3. This we know because patch square in one channel like that you have 3 channels RGB. So total there are such D vectors. If you visualize all the D embedding filters directly, it's too high dimensional and redundant. So PCA is applied to find the few principal components that explain most variance among the filters. Okay. So here what is being shown is not the different channels of the filter. What is being shown, it's not different channels of E. It is when you decompose E into 28 principal components, and E is a matrix, and if you plot those 28 principal components in a matrix format, that is what you are seeing here. All the three RGB is there. Then similarly, the components resemble plausible basis functions for a low dimensional representation of the fine structure within each patch. So each patch contains some structures in the image, and in lower dimensions or in the lower dimensionality space D, maybe these are the basis function which are used to represent the vectors. So you can see that these principal components are trying to capture features of different types. So this is trying to capture whatever grid features there are in the image. This is trying to capture perhaps vertical grids, horizontal grids. Then you can see circular, annular rings. Here there is like a wavy pattern which is at a slanting. So it's very much similar to how convolution filters try to capture different types of features from your input image. So same thing what this E is doing. E will try to capture different features from your input X to convert the X into a D-dimensional representation. But there is one more thing, position embedding, which we are yet to discuss. So let's see. After the projection, a learned embedding learned position embedding is added to the patch representations. So figure 7 shows the model learns to encode distance within the image in the similarity of position embeddings. That's closer patches tend to have more similar position embeddings. This sentence is not very clear, right? But when you see the image, it will be very clear. Look at this. So look at this graph. What you see here on the y-axis is the patch row number. X-axis is the patch column number. And inside each of these cells, what is plotted is the cosine similarity between every patch against every other patch. So what you can see here is, look at the place where the cosine similarity is highest. For the patch number at position 1,1, the cosine similarity is highest over here. For patch at position 2,2, look at the cosine similarity peak. Here, look at the cosine similarity peak, cosine similarity peak, cosine similarity peak, like that, and so on. So although they have plotted the cosine similarity here as a matrix, the way this works is you have, let's say you have n patches, you will have n plus 1 total position embeddings, 1 for the initial classification token. So let's say n equal to 4, you have 4 plus 1, 5. So total you have 5 position embeddings. So we can call it as P1, P2, etc. up to P5. And cosine similarity will be the dot product between Pi and pj, and here I will run from 1 to 5 and j will also run from 1 to 5. And then what they have done here is they have plotted it such that PIPJ, when I runs from 1 to 5 and j runs from 1 to 5, will be 25 numbers. So you can plot that as a 5 by 5 matrix. Here it's not 5 by 5, here it's bigger than that, but essentially that's what they have done. And what you can see here is somehow, although the position embedding is a learnable parameter, it is able to capture the fact that the position number 1,1 is the first patch. Position number 1,5 is the fifth patch in the first row. Because you can see that as you progress in the same row, cosine similarity is shifting from first column, second column, third column. The peak of the cosine similarity is is shifting column wise. Similarly, when you are moving down one column, you can see that the peak of the cosine similarity is shifting row wise. So somehow the spatial position information is automatically getting embedded in this learned position embedding. That's what this graph is trying to show. Now let's go back. Further, the row column structure appears. Patches in the same row / column have similar embeddings, as you can see. So patches in the same row / column have similar embeddings. Finally, a sinusoidal structure is sometimes apparent for larger grids. So that is in the appendix. We'll come to that. That the position embeddings learned to represent 2D image topology explains why handcrafted 2D aware embeddings do not yield any other improvements. Basically, what is being said here is something that was already said in the beginning of the paper, that they tried both learnable position embedding as well as handcrafted 2D aware position embeddings. The 2D aware position embeddings did not give any extra additional benefits because the learnable position embedding was already able to capture the two-dimensional topology, two-dimensional patch information. That's what here they are trying to say. Then, self-attention allows vision transformer to integrate information across the entire image, even in the lowest layers. We investigate to what degree the network makes use of this capability. Specifically, we compute the average distance in image space across which information is integrated based on attention weights. So what we are trying to see here now is, can we visualize whether the attention mechanism in vision transformer is looking at the same pixels that it is supposed to look where the information is there. So here what they do is they construct something called as attention distance, and attention distance is nothing but if, for example, let's say there is this sentence, the teacher, this is an example I took in the beginning, teacher who was teaching a difficult concept to the students, smiled. So here, maybe the average attention score will be tending to be high because, or average distance will be tending to be high because look at the distance between these two tokens, smiled and teacher. They should have very high attention to each other because teacher is the one who is smiling. So the attention score between teacher and smile should be high, but their relative position is far away. Smiled is the last word, teacher is one of the first words in the sentence. So this we can quantify to see what is the distance between patches that are paying most attention to each other based on the attention weights. And this is very similar to a concept called receptive field. So in convolutional neural network, receptive field tells you how big of an area is your convolution filter looking at to produce the output. Similarly, in vision transformer, you don't have an idea of receptive field, but you can define something called as attention distance, where it's the average spatial distance between a patch and the other patches weighted by the attention weights. So let's say I have 9 patches and I want to calculate the attention distance, average attention distance corresponding to this. You calculate what is the attention it's paying to itself, what is the attention weight between that and this, and like that you will have 9 attention scores or 9 attention weights. And then you can also look at what is the distance between these patches. And basically you can construct a attention weighted average of the distance between the patches. So that is the attention distance. We find that some heads attend to most of the image already in the lowest layers. So what does this mean? Some attention heads. So it's a multi-head attention, by the way. In the vision transformer small model, there are 12 parallel attention heads in each transformer block. Like that, there are 12 transformer blocks. So here, when you say the lowest layer, it means the initial transformer blocks, not the later ones. So some attention heads in the initial transformer block, they already have kind of high attention distances, average attention distances, meaning they are already integrating information globally. I will just show you one graph to make this very clear to you. So this is the graph. So here, y-axis is mean attention distance. X-axis is the network depth. So layer number 1, 2, 3, etc. Here it's 20 plus. I guess they are plotting this for, this is for large. This is not for the base model. If it was for the base model, they would have had only 12 layers. Here they have, I think, 24 layers or something. And look at look at this head number 1. The attention head 1 in layer 1, in layer 2, in layer 3, and so on. The mean attention distance is already very high. What does this mean? It means attention head number 1 in all the layers, or in almost all the layers, is already looking at the global, amount of, or how else can we say? The attention head number 1 is already paying attention to farther away patches. So in an attempt to integrate global information. It's not true for all the heads, by the way. Some heads, like these are some other heads. These heads have low mean attention distance in the earlier layers, which means in the earlier layers of the transformer blocks, maybe these heads, maybe this is head number 7, head number 12. These heads are not paying attention to farther away patches. They are maybe paying attention to geometrically closer patches. But eventually, as you go to further and further later layers of the transformer blocks, you can see that all attention heads have a high mean attention distance, which means all attention heads are kind of paying attention to global patch attentions, not like just looking at patches that are close to each other. This is an amazing thing. And this shows that, you're not just locally constrained. The attention mechanism is not locally constrained. So other attention heads have consistently small attention distances in low layers, which we saw. This highly localized attention is less pronounced in hybrid models that apply a ResNet before transformer. So figure 7 right. Let's check figure 7 right. I think this is, I don't think this is a hybrid model. I think this is just a vision transformer. So I'm not sure figure 7 is showing us the ResNet before transformer at all, suggesting that it may serve a similar function as early convolutional layers in CNN. The convolution layers in CNN, what does it do? Convolution layers have locality and translation equivariance. So locality means it helps you pay attention to local features within the receptive field of the convolution filter. So the equivalent of that is being done by the early layers, where some of the heads are having low mean attention distance, which means you are focusing attention in the patches that are geometrically close to each other. But in the later heads, you are integrating everything in a global sense. Globally, we find that the model attends to image regions that are semantically relevant for classification. So this is an interesting sentence, but this interesting sentence is backed up by this figure. Look at this figure. So here they are plotting the input image versus attention rollout. So attention rollout is you take the product of attention weights from all the layers and you can just overlay it on top of the image. And here this bright color region is wherever the attention weights are concentrated. And here you can see that this image is about an aircraft, and the attention weights are also concentrated around that aircraft. This one, I don't know. This one, in this, actually, I can see a snake, but it doesn't seem like attention is focused necessarily around the snake. The first image works really well though. It is like a toy poodle or something like that, some dog breed. And you can see that attention weights are mostly concentrated around that. So it's working really nicely when you plot the attention scores or attention weights. So this part is very easy to do. In code also, it's just a few lines of code. Then self-supervision. Transformers show impressive performance on NLP, which we know. However, much of their success stems not just from excellent ability, excellent scalability, but also from large-scale self-supervised pre-training. Transformers actually were using internet dataset. There are huge datasets and self-supervised training because you don't have explicit labels. The label is the next word itself. Next word that you are supposed to predict in a sentence, that itself will form the label. So this is what BERT was using. This is what transformer architecture in the attention is all you need paper was also using. We also perform a preliminary exploration on masked patch prediction for self-supervision, mimicking the masked language modeling used in BERT. So MLM, masked language model in BERT, where some tokens were replaced with masks. So here, these guys also tried to create something similar to that, where patches were masked and you were trying to predict, not exactly the patches. I'll tell you what they were trying to predict. So for every masked patch, the model would try to predict a certain embedding. Okay. The model's prediction is then compared to the actual patch content that was hidden. The difference is measured using standard mean squared error between the predicted and true pixel values or the embeddings. So in this paper, I think I just got confused between this paper and another paper on vision language model. So on vision language model, they do something slightly different. Maybe when we are doing a paper review on vision language BERT or vision language model paper, we can discuss more about that. But here what they do is, instead of classifying the image in vision transformer using the classification token, so instead of making it a classification task, you can ask the transformer to predict the pixel values associated with a patch. So if a patch is 16 by 16, 256 pixels, the final output that comes out of the vision transformer, we can make it to be 256 numbers. And those numbers we can compare against the actual values inside the patch. So model's prediction is compared to the actual patch content. So actual patch content will be hidden. It will be like a hidden token. And then you can construct an error using just the normal mean squared error. Sigma yi predicted minus yi the whole square, where I runs from 1 to 256 if there are 256 pixels in one patch. With self-supervised pre-training, our smaller vision transform, and why is this called self-supervised? Because there are no labels that you need. You can take any image, you can divide that into patches, and then you can train your model to, let's say your image is divided into 9 patches. You mask one of the patch, you provide 8 patches to your vision transformer, and you ask the vision transformer to predict the pixel values in the 9th patch. So that way it's self-supervised because you are not manually labeling anything. You are constructing your labels, and labels are part of your dataset. So that's why it's called self-supervised learning. And our smaller vision transformer base 16 patch size model achieves 79.9% accuracy on ImageNet, a significant improvement of 2% to training from scratch, but still 4% behind supervised pre-training. So supervised pre-training is, you know, the ImageNet labels and you pre-train, and then you'd see how well the prediction works. So it was, the self-supervised learning was not as good as supervised pre-training. However, in self-supervised learning, you can use, you don't have any limits. You can use any data from the internet. So they say we leave exploration of contrastive pre-training to future work. So contrastive pre-training we will see when we discuss the paper on CLIP, which initially came out from OpenAI. So this was also another famous paper. But let's not go into the details of that. We are almost at the end of the paper now. There is some appendix to cover, which I do plan to cover, but this is the last section. Conclusion. We have explored the direct application of transformers to image recognition. So image recognition means image classification primarily. Unlike prior works using self-attention in computer vision, we do not introduce image-specific inductive biases into the architecture, apart from initial patching. So patching introduces two-dimensionality, of course. It's a two-dimensional operation. But other than that, there is no convolution operation to introduce inductive biases. Otherwise, you could have said that most of the heavy lifting is done by convolution operation. But here, there is no convolution operation. It's purely transformer. Instead, we interpret an image as a sequence of patches and process it by a standard transformer encoder as used in natural language processing. This simple yet scalable strategy works surprisingly well when coupled with pre-training on large datasets like the JFT 300 million dataset. Thus, Vision Transformer matches or exceeds the state of the art on many image classification datasets whilst being relatively cheap to pre-train. We saw this. While these initial results are encouraging, many challenges remain. One is to apply Vision Transformer to other computer vision tasks such as detection and segmentation. So detection is drawing bounding boxes around objects. Segmentation is drawing actual contours around objects. Our results, coupled with those in Carrion et al., I don't know which paper this is, indicate the promise of this approach. So classification is the easiest task to do in images. You have to perform object detection and semantic segmentation or instance segmentation to be able to do more things with computer vision. Another challenge is to continue exploring self-supervised pre-training methods. So self-supervised, we saw like ImageNet 79.9% accuracy. So self-supervised because then you can work on large-scale datasets. Our initial experiments show improvement from self-supervised pre-training, but there is still large gap between self-supervised and large-scale supervised pre-training. Finally, further scaling of Vision Transformer would likely lead to improved performance. How do we know that? Because in the previous graph, in this graph, we saw that the performance even after scaling. So higher models are here on the right hand side of the x-axis because bigger models will require more compute. And you can see that the Vision Transformer performance is not yet stagnating. It's still going up. And this is a logarithmic graph. Please note this. So hopefully what this means is you can simply scale the size of the model and you may get improved performance. So that is the end of the main paper. There is a appendix section which we can quickly go through. I don't think we need to spend too much time. There are a lot of references. Now let's go to the first page in the appendix. So here they are listing the different models and data sets they use to train these models with epochs, base learning rate decay, format, weight decay, everything. This we already saw in the course of reading the paper, but I think it's nice that they have showed it as a table, but I don't think we need to spend any time on this table. Then multi-head self-attention, we know attention function is softmax of query times key transpose divided by square root of dimensionality of the key space or the hidden space in key query value. This is the standard attention, or this is the standard function that was used in attention is all you need paper. And to construct the context vector, it was simply A multiplied by value. So V is value, query key value. Okay, I don't want to spend time on this formula. This is a very famous formula which was proposed in Ashish Vaswani's paper. Attention is all you need. But basically now this is the context vector. And this is the attention weights. And these are the query key value vectors which you get from your original input embedding. So input embedding, you convert to query key value vectors using this transformation: query transformation matrix, key transformation matrix, and value transformation matrix. And then here what you can see is the multi-head self-attention, MSA, where each attention heads operate separately on your incoming input. So input is denoted by Z, output will be denoted. So if input is like Z1, output will be denoted by Z2. So multi-head self-attention is you calculate the self-attention score, and self-attention score is then later multiplied with value to produce the output context vectors. Then table 3 summarizes our training setups. We found strong regularization to be key when training models from scratch. Dropout when used is applied for every layer. So here they are just mentioning some details about training. Grid search over different learning rates. So this is fine tuning. So I don't think we need to, unless we are running these experiments, we need to go into these details. So these are the hyperparameters for fine tuning. In table 3, they were the hyperparameters for pre-training, I guess. Yeah, it was for pre-training. This is for fine tuning. And self-supervision. Yeah, I think this might be interesting. We employ masked patch prediction objective for preliminary self-supervision experiments. So self-supervision means you replace some patches with mask token. To do so, we corrupt 50% of patch embeddings. So not just one patch. So earlier I said out of 9 patches, maybe you will corrupt one patch. But here we corrupt 50% of patch embeddings by either replacing their embeddings with a learnable mask at 80% of the times. So this is exactly what is also done in BERT paper. So you will introduce tokens which are supposed to be mask tokens, and 80% of the times it will indeed be kept as mask tokens. 10% or so times this mask token will be replaced by some other random patches. So you take some patch from an image and replace it with some other random patch, and remaining 10% of the times you will keep it as such. And this itself is done not for all the patches. This is done for 50% of the patches. So 50% of the patches may undergo with 80% probability this, 10% probability this, 10% this. What is this? With 80% probability, it will be replaced with a mask token, 50% of the patches. With 10% probability, it will be replaced with some random token or random patch. With 10% probability, nothing will happen. So that is what they did. This setup is very similar to what is used in Devlin et al. So Devlin et al. Is basically the BERT paper. In BERT paper also they use this. Finally, we predict the 3-bit mean color of every corrupted patch using their respective patch representation. Finally, we predict 3-bit. Yeah, 3-bit, I guess, because RGB mean color. What do they mean by mean color? Let me ask ChatGPT. What does it mean by mean color here? I thought they were predicting the patch values and then we can take mean squared error with the actual patch. But here I'm not sure what exactly they mean by mean color. Okay, so here mean color refers to average RGB color of a patch. Okay, so I don't think they predict R, G, and B. They just predict the mean of these 3 colors, I guess. The model only predicts the 3-bit mean color. Okay, so then that makes sense. So totally, if there is, there are totally how many 16 by 16 pixels, which is 256. It won't be 256 by 3. They will be predicting 256 numbers of every corrupted patch using the respective patch representation. We train our self-supervised model for 1 million steps with batch size of 4096 on JFT dataset. We use Adam. These are details of the self-supervised training. Last, we would like to remark that our instantiation of mask patch prediction does not require such an enormous amount of pre-training. Okay, this is also fine. Additional result, we report detailed results corresponding to the figures present in the paper. Okay, let me see what other tables do they have. Okay, so this is pre-training dataset, pre-training dataset, pre-training dataset. This is fine-tuning, 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 fine-tuning. So you have 1, 2, 3, 4, 5 models. All of them are vision transformer. This is base model, large, huge. Then 16 is the patch size, 32 is the patch size, 16 patch size, 32 patch size, 14 patch size. So these 5 models are fine-tuned on these 1, 2, 3, 4, 5, 6 fine-tuning datasets. But pre-training is either done on ImageNet or ImageNet 21K or JFT 300 million. And some clear trends you will be able to see. So JFT 300 million, of course, the bigger model will have a better performance. You can see that. So in general, numbers in this column will be the highest. So see 99.5, these are all less than that. 94.55, these are all less than that. So for biggest dataset pre-training, the biggest model will be the best. But for smaller datasets, so for ImageNet, it is not, first of all, this huge model, they did not pre-train on the smallest ImageNet 1K dataset. But let's compare between large and base. See here, the base model is performing better than all other models for the smallest data. So here also base model is performing the best. Here also base model is performing the best. Same here. No. Here for Oxford alone, this large model is performing the best. It's an exception. But here also base model is performing the best. So in general, you can see that the performance of the model for smaller data sets, smaller model is performing better. Among the vision transformers, we are not comparing vision transformers with ResNet or CNN. Among the vision transformers, for smaller data sets, smaller vision transformers are better. But for larger data sets, larger vision transformers are better. And here it is again comparison between different vision transformers against ResNet and hybrid models. So this is hybrid, because here it's ResNet with the features extracted and fed to vision transformer. This is purely CNN, and this is vision transformer. Here also you will see the trend that hybrid and CNN will perform almost similar on bigger data sets. So what is a big data set? Actually, none of these are big data sets. These are all, I guess, fine tuning. And you can see that, so you can see that big models which have higher exaflops. So vision transformer huge. These two models have 1500 to 4200 exaflops of computation. CNN in that range of computation. Hybrid in this range of computation. So if you look at models of similar computation, so let's say this guy versus this guy versus this guy, performance of hybrid and vision transformer should be similar. Let's see, 99.11 versus 99.56, whereas the performance of CNN should be a little bit lower. You see, performance of CNN is a little bit lower. So this is this we had already seen in that plot where x-axis was exaflops and y-axis was the accuracy. Okay, additional analysis, stochastic gradient descent versus Adam, which I don't think is of too much relevance right now. Transformer shape, we ran ablation on scaling different dimensions. So this we already saw. Ablation means you are basically controlling different aspects. You're only modifying one component at a time. So you either change the number of layers or you change the hidden dimensionality, etc. So ablation studies is very, very commonly done in large language models. We can see that scaling the depth results in biggest improvement, which are clearly visible up to 64 layers. And this is shown in which figure? They are not meant, figure 8. So figure 8 is this, scaling different model dimensions of vision transformer. So here you can see that for ImageNet 5 shot, relative compute means bigger models are seen on the right hand side. As you go up in model size or compute, the accuracy also increases, but depth is all getting saturated. See here, depth has a saturation effect after some certain compute exaflops. So I think that's what they are trying to say here. We can see that scaling the depth results in biggest improvements, which are clearly visible up until 64 layers. So depth is having a much more rapid effect. So the slope of d by d compute of accuracy is highest for the depth. So because if you increase the depth, and that will result in increase in the relative compute, you have the highest changes. So if you increase the depth such that relative compute is increasing this much, you have so much improvement in accuracy. So but up until around this points. And what is this? So this is 1, this is 10, 20, 30, 40, 50, 60, up to 60. So this is 60. Maybe that is what they are saying. We can see that scaling the depth results in biggest improvement, which are clearly visible up to 64, up until 64 layers. Okay, it's not 60, it's 64 to be exact. However, diminishing returns are already visible after 16 layers. Let's see where is the diminishing return. So this is roughly 16, this number. After that, it's like almost closing, like it's plateauing, right? Okay, so basically increasing the depth is better, but with diminishing returns. Interestingly, scaling the width of the network seems to result in smallest changes. Where do we see that? scaling the width. Let me just delete this. See, width is this purple curve, and it has the smallest slope among this. So to see this much improvement in accuracy, you have to change the width so much that computation cost is increasing by this much. So whichever line has the smallest slope, that is the parameter which has the least effect on improvement in accuracy. So here the smallest slope is on width. So width has the least effect, depth has the highest effect. Overall, we find that scaling all dimensions proportionally result in robust improvements. Okay, then what else? Head type and class token. In order to stay as close as possible to original transformer, we made use of an additional CLS or class token, which is taken as the image representation. We know this already. The output of this token is then transformed into a class prediction via MLP. So this we know in the vision transformer image. Once the CLS token come out of the transformer block, it is passed through a multi-layer perceptron, which is the classification head, which uses tan hyperbolic as the activation function. This design is inherited from the transformer model for text, and we use it throughout the main paper. An initial attempt at using only image patch embedding, global average pooling, followed by linear classifier, just like ResNet, performed very poorly. So initial attempt at using only image patch embeddings, global average pooling, and then followed by linear classifier. So however, we found that this is neither due to extra token nor due to gap operation, not due to global average pooling operation. Instead, it was the difference in performance, which is explained through different learning rate. So this was actually the most confusing graph for me in the paper. Anyway, it's not of much significance, but what they're saying is, when they did something like this, when they used only image patch embeddings without adding the extra classification token, and then they use global average pooling and then use the linear classifier. So linear classifier, I hope this is multi-layer perceptron. Similar to ResNet's final feature map, it performed very poorly compared to when you had the classification token. So the classification token is very important to perform the or to capture the final image embedding properly. But they said the difference is not because of any of this. The difference is due to learning rate. And then they show this graph. So this is a little bit, I thought, but then if that was the case, why don't you run for the same learning rate so that you can have apples to apple comparison? Because here you can see that when you have CLS token and learning rate equal to 8 times 10 to the power of minus 4, this is the blue curve, okay? When CLS token is there, accuracy is high. But when you have global average pooling with a learning rate of 3 times 10 to the power of minus 4, you have, or rather, when you have global average pooling with 8 times 10 to the power of minus 4, which is the same learning rate, by the way, you have so much difference in accuracy between these two curves. But then if you keep the learning rate a bit smaller, 3 times 10 to the power of minus 4, your accuracy increases. So I was not sure what exactly are they trying to say. Isn't this showing that if you keep the learning rate a little bit lower, which will make it apples to orange comparison, because if you really want to compare these two graphs, you should compare the ones with same learning rate. So this blue curve and orange curve, these two are the same learning rate, this and this. Then I agree, yes, the one with the class token performs better compared to the one without that. This is the one without, this is the one with global average pooling. That I get. But if you slightly reduce the learning rate, your performance is now, this is again gap, but with a slightly lower learning rate. Instead of 8 times 10 to the power of minus 4, this is 3 times 10 to the power of minus 4. So I was not really sure whether the argument is very strong to say that actually class token is so important. Maybe you don't need class token. You can get the representation of the image from one of the other tokens by global average pooling. Let's not go into the details of how exactly global average pooling is implemented here. But let's just we're just trying to think, is the classification token really necessary or not? And from this graph, it seems like, to me, it's not really necessary. We can figure out ways to make this work without classification token also. And then in one of the last parts of the paper, they talk about 3 ideas. 4 different types of embedding. So one with no position embedding, one-dimensional position embedding, two-dimensional position embedding, and then relative positional embedding. I don't think we need to spend too much time on this. This is just, I would say, they're playing a little bit with different types of position embeddings to see what is the impact. And in summary, there is not too much impact, is what you can see from the paper. Then I think, yeah, that's pretty much it. Empirical computation cost. Yeah, so then they show some computation cost, axial attention. I think the rest of the things are a little bit, not really relevant for today's discussion. They are just supplementary material. Yeah, so the attention map, which you saw, the aeroplane with attention map shown around the aeroplane, it was created using a technique called attention rollout. So you can multiply attention weights matrices from all different layers of transformer blocks, and then you can create a attention rollout score, which you can superimpose on top of the images to see how the attention scores or multiplication of attention weights are looking when you are plotting it on top of images. VTAB breakdown, I think these things are fine. And in the last page, this is the last page of the paper where they are showing the attention score. I think this page had a better resolution. I don't know why it's looking a little bit pixelated. Yeah, now it's better. So here you can see that this is the actual image, and here the attention weight distribution. This is the actual image, this monkey. Here the attention weight distribution is concentrated around here. This is the actual image, this car, and here you can see the attention weights are concentrated around this region. So clearly we can see that the model is actually looking at things that it is supposed to look, which is a very encouraging thing. And this is the last page of the paper. So although I have skipped a little bit of extra details in the supplementary section, which you can read yourself, it's anyway not going to impact your understanding of the paper. We have covered pretty much the whole paper in a lot of detail. So that's the conclusion of the dissection of vision transformer paper. I hope you understand about vision transformer architecture much better than before. That's the number one hope that I have. Second thing is, we have gone through pretty much the entire paper, at least the main paper part. Appendix part, some parts we have skipped, but the main paper we went through in a lot of detail. So I read it line by line and I was trying to explain in the best possible way, but of course I might have skipped some details and I might have made errors here and there, which is very likely to happen when you are reading a very long technical paper. But what you can do is you can also do something like that. You keep the paper on your side, printed copy, go through it line by line, have ChatGPT or some sort of AI tool or something to assist you in clearing your doubts. So that way you can have a very proactive experience in reading, plus at the same time clearing your questions. That way your learning can be much faster. But I hope this lecture at least showed you a pathway for how to read AI ML research papers and how to effectively make use of tools like ChatGPT to read and understand papers. You will not know everything at once, right? There are many concepts that this paper is referring to from the previous papers that are already published in the literature. So in such cases, you definitely need some sort of assistance. You won't always be able to go to that paper and read it, because that will prolong your goal of reading the paper that you are reading currently. So you will end up in a spiral if you start doing that. Of course, sometimes you will have to go back and refer to some other papers. You have to actually read it, which we will do in the current series. I do plan to cover the seminal paper on BERT model sometime later, on vision language model, on perhaps at some point I'll also cover the attention is all you need paper, just like this. But I hope today's lecture gave you a pathway for you also to do the same. I know that this lecture has been very, very long. That's why I mentioned at the start of the series, I have no idea what the length of each lecture is going to be. It entirely depends on the length of the paper. And I wanted to make it a point not to dilute it down or not to split it into different parts, which is the reason why I posted this lecture as one single piece. I hope if you have reached this point, I hope you are fairly tired, which is expected to happen, but also you feel incredibly rewarding. And now if you are reading the paper yourself, I am pretty sure you will find a lot more confidence to read it yourself. So thank you so much for listening to this very, very long lecture. And thank you for finishing all the way till here. I hope you are deriving immense satisfaction from this activity. And I'm looking forward to seeing you again in the future lectures in this series. Thank you so much. Take care and see you soon.